In the vast expanse of the universe, where countless mysteries reside, lies the story of our very own star, the Sun. This tale begins in a region of space known as a molecular cloud, a colossal collection of gas and dust particles. But how does such a cloud give rise to a star as magnificent as the Sun? Let's delve into the fascinating process of stellar formation, focusing on the birth of our Sun. Molecular clouds, also referred to as stellar nurseries, are the coldest and densest parts of the interstellar medium. They are primarily composed of hydrogen molecules, along with helium and trace amounts of heavier elements. These clouds can span light years across and contain enough material to form thousands of stars. But what triggers the transformation of this seemingly inert cloud into a blazing star? The process begins with a disturbance, often caused by nearby supernova explosions or the gravitational influence of passing stars. These disturbances create shock waves that compress parts of the molecular cloud, increasing its density. As the cloud compresses, regions within it, known as clumps, begin to collapse under their own gravity. This marks the first step in the formation of a protostar. As the clump collapses, it fragments into smaller regions called cores. Within these cores, the material continues to fall inward, and the core's density and temperature rise. This is where the magic begins. As the core contracts, it spins faster due to the conservation of angular momentum, much like a figure skater pulling in their arms to spin faster. This spinning motion flattens the material into a rotating disk surrounding the core. At the heart of this disk, the temperature and pressure become so intense that nuclear fusion ignites. Hydrogen atoms begin to fuse into helium, releasing an enormous amount of energy in the form of light and heat. This marks the birth of a new star, a protostar, which will eventually become our Sun. But the journey from a protostar to a fully fledged star is not instantaneous. It takes millions of years for the protostar to accumulate enough mass and for nuclear fusion to stabilize. During this time, the protostar is surrounded by a circumstellar disk of gas and dust, which may eventually form planets, moons, and other celestial bodies. As the protostar continues to gather material from its surroundings, it grows in size and luminosity. The energy produced by nuclear fusion creates an outward pressure that counteracts the inward pull of gravity. When these forces reach equilibrium, the star enters the main sequence phase of its life cycle, where it will spend the majority of its existence. Our Sun, now a main sequence star, shines brightly in the sky, providing the energy necessary for life on Earth. But what makes the Sun so special compared to other stars? For one, its size and temperature are just right to support life as we know it. The Sun is classified as a G-type main sequence star, or a G-dwarf, which means it is relatively stable and has a lifespan of about 10 billion years. Moreover, the Sun's position in the Milky Way galaxy is ideal. It resides in a region known as the galactic habitable zone, where conditions are favorable for the development of life. This zone is neither too close nor too far from the galactic center, avoiding the dangers of high radiation levels and frequent supernovae. As we reflect on the birth of our Sun, we can't help but marvel at the intricate processes that govern the universe. From a simple cloud of gas and dust, a magnificent star was born, setting the stage for the emergence of life on Earth. But what lies ahead for our Sun? How will it evolve over the billions of years to come? These questions lead us to the next chapter in the Sun's life story, where we will explore its future and the eventual fate of our solar system. Stay tuned as we continue this cosmic journey, unraveling the mysteries of the universe one star at a time. In the previous act, The Birth of Our Star, we delved into the fascinating process of the Sun's formation. This journey took us back to a time when a massive cloud of gas and dust, known as a solar nebula, collapsed under its own gravity. This collapse initiated nuclear fusion at the core, giving birth to our Sun, the central star of our solar system. The Sun's formation was a pivotal event that set the stage for the creation of the planets and other celestial bodies orbiting it. We shift our focus from the Sun to the closest planet in its orbit, Mercury. Mercury is a planet of extremes, known for its scorching temperatures and barren landscape. But what makes Mercury so unique? And why is it so different from the other planets in our solar system? Mercury is the smallest planet in our solar system and the one closest to the Sun, orbiting at an average distance of about 58 million kilometers, 36 million miles. Its proximity to the Sun means that it experiences some of the most extreme temperature variations of any planet. During the day, temperatures on Mercury's surface can soar to a blistering 430 degrees Celsius, 800 degrees Fahrenheit. However, without a significant atmosphere to retain heat, nighttime temperatures can plummet to a frigid minus 180 degrees Celsius, minus 290 degrees Fahrenheit. This dramatic temperature fluctuation is due to Mercury's thin atmosphere, or exosphere, which is composed mostly of oxygen, sodium, hydrogen, helium, and potassium. Unlike Earth's atmosphere, Mercury's exosphere is not dense enough to trap heat, leading to these extreme temperature swings. But why does Mercury have such a thin atmosphere? One reason is its small size and low gravity, which makes it difficult for the planet to retain a thick atmosphere. Additionally, its proximity to the Sun means that solar winds constantly strip away any gases that might accumulate. Mercury's surface is another point of interest. It is heavily cratered, resembling our moon more than any other planet in the solar system. This resemblance is due to the lack of geological activity on Mercury, which means that craters formed by asteroid impacts have remained unchanged for billions of years. The planet's surface is also marked by large plains and cliffs, known as scarps, which are believed to have formed as the planet's core cooled and contracted. One of the most intriguing features of Mercury is its large iron core, which makes up about 85% of the planet's radius. This core is proportionally larger than that of any other planet in the solar system. Scientists believe that this could be due to a massive collision with another celestial body early in the planet's history, which stripped away much of its original crust and mantle, leaving behind the dense core. Mercury's orbit is another fascinating aspect to consider. It is the most elliptical of all the planets, meaning that its distance from the Sun varies significantly over the course of its orbit. This elliptical orbit, combined with its slow rotation, results in a unique phenomenon known as a double sunrise. Observers on Mercury would see the Sun rise, set, and rise again in certain areas of the planet due to this peculiar orbital pattern. Despite its proximity to the Sun, Mercury is not the hottest planet in our solar system. That title goes to Venus, which, thanks to its thick atmosphere, experiences a runaway greenhouse effect that keeps its surface temperatures consistently hotter than those on Mercury. Nevertheless, Mercury's extreme temperatures and lack of atmosphere make it a challenging environment for exploration. NASA's MESACGER mission, which orbited Mercury from 2011 to 2015, provided valuable insights into the planet's composition, geology, and magnetic field. One of the surprising discoveries made by MESACGER was the presence of water ice in permanently shadowed craters at Mercury's poles. This finding suggests that even in the harshest environments, water can exist in some form. As we explore Mercury's scorched surface, we are reminded of the diverse and dynamic nature of our solar system. Each planet, including Mercury, offers unique insights into the processes that shaped our cosmic neighborhood. What other secrets might Mercury hold, and how can they help us understand the formation and evolution of planets? As we continue our journey through the solar system, these questions will guide our exploration and deepen our appreciation for the wonders of the universe. We delve into the fascinating and hostile environment of Venus, a planet often referred to as Earth's twin due to its similar size and composition. However, despite these similarities, Venus presents a stark contrast to Earth, earning its reputation as an evil twin. This act focuses on understanding the toxic atmosphere and the runaway greenhouse effect that makes Venus one of the most inhospitable places in our solar system. Venus is the second planet from the Sun and is shrouded in a thick, toxic atmosphere composed predominantly of carbon dioxide, with clouds of sulfuric acid. This dense atmosphere creates a surface pressure that is over 90 times that of Earth, equivalent to the pressure found 900 meters underwater on Earth. Imagine standing on the surface of Venus. The pressure would crush you instantly, and the heat would incinerate you. But what causes such extreme conditions on Venus? The key factor is the greenhouse effect, a process that occurs when a planet's atmosphere traps heat from the sun. On Earth, the greenhouse effect is essential for maintaining temperatures that support life. However, on Venus, this process has spiraled out of control. The thick carbon dioxide atmosphere traps heat so effectively that surface temperatures soar to around 475 degrees Celsius, about 900 degrees Fahrenheit, hotter than the surface of Mercury, despite Venus being further from the sun. But how did Venus end up with such a hostile environment? Scientists believe that Venus may have once had oceans similar to Earth. However, as the sun's intensity increased over billions of years, any water on Venus would have evaporated. Water vapor is a potent greenhouse gas, and its presence in the atmosphere would have exacerbated the greenhouse effect, leading to even higher temperatures. Eventually, the water vapor would have been broken down by solar radiation, with the hydrogen escaping into space and the oxygen reacting with surface materials. The clouds of sulfuric acid on Venus add another layer of hostility. These clouds are formed by volcanic activity, which releases sulfur dioxide into the atmosphere. This sulfur dioxide reacts with water vapor to form sulfuric acid clouds, creating a highly corrosive environment. The presence of these clouds also contributes to the planet's high albedo, meaning it reflects a significant amount of sunlight. Despite this, the greenhouse effect is so strong that it still results in extremely high surface temperatures. Venus's atmosphere is also notable for its superrotation, where the entire atmosphere circles the planet in just 4 Earth days, much faster than the planet's rotation period of 243 Earth days. This phenomenon is not fully understood, but it contributes to the complex and dynamic weather patterns observed on Venus. The exploration of Venus provides valuable insights into the potential future of Earth. The runaway greenhouse effect on Venus serves as a cautionary tale about the impact of unchecked greenhouse gas emissions. Could Earth face a similar fate if we do not address climate change? This question underscores the importance of studying Venus and understanding the processes that led to its current state. Despite its inhospitable conditions, Venus remains a target of scientific interest. Missions like the European Space Agency's Venus Express and Japan's Akatsuki orbiter have provided valuable data about the planet's atmosphere and surface conditions. Future missions aim to further explore Venus, potentially uncovering more about its geological history and the possibility of past habitability. As we continue to explore our solar system, Venus stands out as a reminder of the delicate balance required to maintain a habitable planet. Its extreme conditions challenge our understanding of planetary science and highlight the importance of protecting our own planet from similar fates. What more can we learn from Venus, and how can it inform our actions here on Earth? These are the questions that drive scientists to continue their exploration of Earth's evil twin. In the previous act, we delved into the harsh and hostile environment of Venus, often referred to as Earth's evil twin. We explored the planet's thick, toxic atmosphere composed primarily of carbon dioxide, with clouds of sulfuric acid creating a runaway greenhouse effect. This effect traps heat, leading to surface temperatures hot enough to melt lead. The examination of Venus served as a stark reminder of what happens when a planet's atmospheric conditions spiral out of control, offering a cautionary tale of climate extremes. We shift our focus back to Earth, a planet that, unlike Venus, has managed to maintain a delicate balance that supports life. But what exactly makes Earth so uniquely habitable? What are the conditions that have allowed life to not only emerge, but to thrive on this blue planet? One of the key factors is Earth's position in the solar system, often referred to as the Goldilocks zone or the habitable zone. This is the region around a star where conditions are just right, not too hot and not too cold, for liquid water to exist on a planet's surface. Water, as we know, is essential for life as it acts as a solvent, a medium for chemical reactions, and a means of transporting nutrients and waste products. Without liquid water, life as we understand it would not be possible. But Earth's location is just the beginning. The planet's atmosphere plays a crucial role in maintaining its habitability. Unlike Venus, Earth's atmosphere is composed of a balanced mix of gases, including nitrogen, oxygen, carbon dioxide, and trace amounts of other gases. This composition is vital for several reasons. Oxygen is necessary for the survival of most life forms, while carbon dioxide, though present in much smaller quantities than on Venus, is essential for photosynthesis, the process by which plants convert sunlight into energy. The presence of a magnetic field is another critical factor. Earth's magnetic field protects the planet from harmful solar and cosmic radiation. Without this protective shield, life on Earth would be exposed to high levels of radiation, which could be detrimental to living organisms. Moreover, Earth's climate system is regulated by the greenhouse effect, but unlike Venus, it is a balanced greenhouse effect. This natural process involves greenhouse gases like carbon dioxide and methane trapping some of the sun's heat, keeping the planet warm enough to support life. However, the levels of these gases are kept in check by natural processes, such as the carbon cycle, which involves the absorption and release of carbon dioxide by the oceans, forests, and other ecosystems. The planet's geological activity also contributes to its habitability. Plate tectonics, the movement of Earth's lithospheric plates, plays a significant role in the carbon cycle and helps regulate the planet's climate over geological timescales. Volcanic eruptions release carbon dioxide into the atmosphere, while weathering of rocks on the Earth's surface removes it, maintaining a balance that prevents extreme climate conditions. The presence of a large moon is another factor that has contributed to Earth's stable environment. The moon's gravitational pull stabilizes the tilt of Earth's axis, which in turn stabilizes the climate by preventing extreme variations in temperature. This stability has allowed life to evolve and adapt over millions of years without facing catastrophic climate shifts. Furthermore, Earth's biodiversity is both the result of and a contributor to its habitability. The diversity of life forms on Earth creates complex ecosystems that are interconnected and interdependent. These ecosystems play a crucial role in regulating the planet's climate and maintaining the balance of gases in the atmosphere. For example, forests act as carbon sinks, absorbing carbon dioxide and releasing oxygen, while oceans regulate temperature and support a vast array of marine life. But what about the future? As we continue to explore the unique conditions that make Earth habitable, we must also consider the impact of human activities on this delicate balance. The burning of fossil fuels, deforestation, and other activities have led to an increase in greenhouse gases, contributing to global warming and climate change. This raises important questions about the sustainability of our current way of life and the steps we need to take to preserve the planet's habitability for future generations. In conclusion, Earth's perfect balance is the result of a combination of factors, from its position in the solar system to its atmospheric composition, magnetic field, geological activity, and biodiversity. Each of these elements plays a crucial role in creating and maintaining the conditions necessary for life. As we continue to study our planet and learn from its history, we gain valuable insights into the importance of preserving this balance and the potential consequences of disrupting it. What lessons can we learn from Earth's ability to sustain life? And how can we apply these lessons to ensure a sustainable future for our planet? We explored the delicate and unique conditions that make our planet habitable. We delved into the factors that contribute to Earth's ability to support life, such as its optimal distance from the sun, the presence of water, a protective atmosphere, and a magnetic field that shields us from harmful solar and cosmic radiation. These elements work together in harmony to create an environment where life can thrive. We also touched upon the importance of biodiversity and ecosystems in maintaining this balance. highlighting how interconnected and interdependent life on Earth truly is. We shift our focus to our neighboring planet Mars. Mars has long been a subject of fascination and intrigue, not just for scientists, but for the general public as well. Known as the Red Planet due to its reddish appearance, Mars has been the target of numerous missions aimed at uncovering its secrets. But what makes Mars so intriguing? Why do we invest so much effort into exploring this distant world? One of the primary reasons for our interest in Mars is the potential for past life. Scientists have long speculated that Mars may have once harbored conditions suitable for life. Evidence suggests that Mars had liquid water on its surface in the past, a key ingredient for life as we know it. The presence of ancient river valleys, lake beds, and minerals that form in the presence of water all point to a wetter, potentially habitable past. Could Mars have supported microbial life during this time? And if so, what happened to it? The search for past life on Mars involves studying its geology and climate history. By analyzing rock samples and surface features, scientists hope to uncover clues about the planet's past environment. The discovery of organic molecules by the Curiosity rover, for example, has provided tantalizing hints that Mars may have had the right conditions for life. However, finding definitive evidence of past life remains a significant challenge. In addition to the search for past life, Mars is also a prime candidate for future colonization. As Earth's resources become increasingly strained, the idea of establishing a human presence on another planet becomes more appealing. Mars, with its relatively close proximity and similarities to Earth, presents a viable option for human settlement. But what would it take to colonize Mars? What challenges would we face in creating a sustainable living environment on the Red Planet? One of the biggest hurdles in colonizing Mars is its harsh environment. Mars has a thin atmosphere composed mostly of carbon dioxide, with very little oxygen. This means that any human settlement would need to be equipped with life support systems to provide breathable air. Additionally, the surface of Mars is exposed to high levels of radiation due to the lack of a protective magnetic field and atmosphere. This poses a significant risk to human health, necessitating the development of protective habitats and technologies. Another challenge is the availability of resources. While Mars has water ice, accessing and utilizing it for drinking, agriculture, and fuel production would require advanced technology and infrastructure. The concept of in situ resource utilization, ISRU, is crucial for Mars colonization as it involves using local resources to support human activities. This could include extracting water from the soil, producing oxygen from carbon dioxide, and using Martian regolith to build structures. Transportation to and from Mars is another significant consideration. Current technology allows for robotic missions to reach Mars, but sending humans is a much more complex endeavor. The journey to Mars takes several months, and the return trip poses additional challenges. Developing reliable and efficient spacecraft that can safely transport humans to Mars and back is a critical step in making colonization a reality. Despite these challenges, the potential benefits of colonizing Mars are immense. Establishing a human presence on Mars could provide valuable scientific insights, inspire technological advancements, and serve as a stepping stone for further exploration of the solar system. It could also offer a backup location for humanity in the event of a global catastrophe on Earth. As we continue to explore Mars, each mission brings us closer to understanding the Red Planet's mysteries and assessing its potential for supporting life. From the early flybees and landers to the sophisticated rovers and orbiters of today, our exploration of Mars has been a journey of discovery and innovation. What new findings will the next mission reveal? How will our understanding of Mars evolve in the coming years? We invite you to join us on this exciting journey of exploration and discovery. As we investigate the potential for past life and future colonization on Mars, we encourage you to ponder the possibilities and challenges that lie ahead. What will we find beneath the surface of the Red Planet? How will our efforts to explore and possibly inhabit Mars shape the future of humanity? The answers to these questions may redefine our place in the universe and open new chapters in the story of human exploration. The asteroid belt, we embark on a fascinating journey through the vast region of space located between the orbits of Mars and Jupiter. This area, known as the asteroid belt, is a region filled with rocky remnants from the early solar system. These remnants, or asteroids, are pieces of rock and metal that never coalesced into a planet. But why did these materials fail to form a planet? And what can they tell us about the history of our solar system? The asteroid belt is home to millions of asteroids, ranging in size from tiny pebbles to massive bodies hundreds of kilometers across. The largest of these is Ceres, a dwarf planet that makes up nearly a third of the asteroid belt's total mass. Ceres is unique because it is the only object in the asteroid belt that is rounded by its own gravity, distinguishing it from the irregular shapes of most other asteroids. One of the key questions scientists seek to answer is why the asteroid belt exists in its current form. The prevailing theory is that the gravitational influence of Jupiter, the largest planet in our solar system, prevented these materials from coalescing into a planet. Jupiter's immense gravity stirred up the region, causing collisions and preventing the accretion of a larger planetary body. This theory highlights the dynamic and sometimes chaotic nature of our solar system's formation. The study of asteroids is not just about understanding the past. It also has implications for the future. Asteroids are considered to be time capsules that hold clues to the conditions and processes that were present in the early solar system. By studying their composition, scientists can gain insights into the building blocks of planets and the origins of water and organic materials on Earth. Could these rocky bodies hold the secrets to the origins of life itself? Moreover, the asteroid belt presents opportunities for future space exploration and resource utilization. Some asteroids contain valuable metals and minerals, such as iron, nickel, and even precious metals like gold and platinum. The concept of asteroid mining has been gaining traction as a potential means to obtain resources that are becoming scarce on Earth. But how feasible is it to mine asteroids, and what technological advancements would be necessary to make it a reality? In addition to their scientific and economic potential, asteroids also pose a threat to Earth. Throughout history, impacts from asteroids have had significant effects on our planet, including the extinction of the dinosaurs. Understanding the orbits and characteristics of asteroids is crucial for assessing the risk of future impacts and developing strategies for planetary defense. What measures are currently in place to detect and mitigate potential asteroid threats? And how can we improve our preparedness for such events? As we journey through the asteroid belt, we also encounter the diverse range of asteroid types. These include carbonaceous asteroids, which are rich in carbon and water, and metallic asteroids, which are composed primarily of metal. There are also silicate asteroids, which are made up of silicate minerals. Each type of asteroid offers different insights into the materials and processes that were present in the early solar system. The exploration of the asteroid belt is not just a theoretical endeavor. Several space missions have been launched to study asteroids up close. NASA's Dawn mission, for example, visited both Vesta and Ceres, providing valuable data about their composition and history. More recently, the OSIRIS-REx mission successfully collected samples from the near-Earth asteroid Bennu, which are expected to provide further insights into the building blocks of our solar system. As we delve deeper into the mysteries of the asteroid belt, we are reminded of the interconnectedness of our solar system. The study of asteroids not only enhances our understanding of the past, but also informs our plans for the future. Whether it is through the potential for resource utilization, the assessment of impact risks, or the quest to uncover the origins of life, the asteroid belt remains a region of immense scientific interest and potential. What new discoveries await us in the asteroid belt? How will our understanding of these rocky remnants shape the future of space exploration and our place in the universe? As we continue our journey, these questions drive our curiosity and inspire us to explore the unknown. The asteroid belt, with its countless mysteries and possibilities, remains a testament to the wonders of our solar system and the endless pursuit of knowledge. We delve into the fascinating world of the largest planet in our solar system, Jupiter. This act focuses on exploring the massive gas giant and its most iconic feature, the Great Red Spot, a storm that has been raging for centuries. Jupiter is a gas giant, which means it doesn't have a solid surface like Earth or Mars. Instead, it is composed mainly of hydrogen and helium, similar to the Sun. This composition gives Jupiter its distinct appearance, with swirling clouds and bands of different colors. These bands are created by strong winds that blow in opposite directions at different latitudes, creating a stripe pattern across the planet. One of the most intriguing aspects of Jupiter is its Great Red Spot. This is a massive storm, larger than Earth itself, that has been observed for over 350 years. The storm is an anticyclonic storm, meaning it rotates in the opposite direction of the planet's rotation. Scientists believe that the Great Red Spot is driven by Jupiter's internal heat, which causes the gases in the atmosphere to rise and create powerful winds. The Great Red Spot is not only massive in size, but also in longevity. It has persisted for centuries, although it has been shrinking in recent decades. This raises questions about the future of the storm. Will it eventually dissipate, or will it continue to rage on for centuries to come? Scientists are using advanced telescopes and spacecraft to study the storm and gather data to help answer these questions. Jupiter's atmosphere is a turbulent place, with storms and winds that can reach speeds of up to 400 miles per hour. The planet's rapid rotation, completing a full rotation in just under 10 hours, contributes to this turbulence. This rapid rotation also causes the planet to bulge at the equator, giving it an oblate shape. In addition to the Great Red Spot, Jupiter is home to many other storms and atmospheric phenomena. The planet's atmosphere is divided into several layers, each with its own unique characteristics. The uppermost layer is the troposphere, where most of the weather activity occurs. Below that is the stratosphere, followed by the thermosphere and exosphere. Jupiter's magnetic field is another fascinating aspect of the planet. It is the strongest of any planet in the solar system, about 20,000 times stronger than Earth's. This magnetic field creates intense radiation belts around the planet, which can pose a hazard to spacecraft and any potential future missions to explore Jupiter's atmosphere. The exploration of Jupiter and its Great Red Spot is not only important for understanding the planet itself, but also for gaining insights into the dynamics of gas giants in general. These massive planets are common in our galaxy, and studying Jupiter can help us learn more about the formation and evolution of other planetary systems. As we continue to explore Jupiter, we are also learning more about its many moons. Jupiter has at least 79 known moons, with the four largest being the Galilean moons, Io, Europa, Ganymede, and Callisto. Each of these moons is unique and presents its own set of mysteries to unravel. For example, Europa is believed to have a subsurface ocean beneath its icy crust, making it a prime candidate for the search for extraterrestrial life. The study of Jupiter and its Great Red Spot is an ongoing endeavor, with new discoveries being made all the time. As technology advances, we are able to gather more detailed data and gain a deeper understanding of this fascinating planet. What new secrets will we uncover about Jupiter and its Great Red Spot in the future? How will these discoveries shape our understanding of the solar system and beyond? The exploration of Jupiter is a journey that continues to captivate scientists and space enthusiasts alike, and there is still much to learn about this giant of the solar system. In this act, we turn our gaze from the turbulent atmosphere of Jupiter to the serene and captivating beauty of Saturn, the sixth planet from the Sun. Saturn is perhaps best known for its stunning ring system, which sets it apart from all other planets in our solar system. These rings are not only visually striking, but also scientifically intriguing, offering a wealth of information about the planet itself and the broader processes at play in our solar system. Saturn's rings are composed primarily of ice particles, with a smaller amount of rocky debris and dust. These particles range in size from tiny grains to massive chunks as large as mountains. But what exactly are these rings made of, and how did they come to be? The composition of Saturn's rings has been a subject of study for many years. The ice that makes up the majority of the rings is thought to be water ice, similar to the ice found on Earth. This ice reflects sunlight, which is why the rings appear so bright when viewed from Earth. The presence of rocky material suggests that the rings may have formed from the remnants of a moon or comet that was shattered by Saturn's gravity. The origin of Saturn's rings is still a topic of debate among scientists. One theory suggests that the rings are remnants of a moon that was destroyed by a collision with a comet or asteroid. Another possibility is that the rings formed from the debris left over from the formation of Saturn itself. Some scientists even propose that the rings are relatively young, perhaps only a few 100 million years old, while others believe they could be as old as the planet itself. Saturn's rings are not a single continuous structure, but are instead made up of thousands of individual ringlets. These ringlets are separated by gaps, the most famous of which is the Cassini division, a dark band that separates the A and B rings. The Cassini division is not empty, but contains a lower density of particles than the surrounding rings. The rings are also incredibly thin, despite their vast expanse. In some places, they are only about 10 meters thick. This thinness is due to the fact that the particles in the rings are confined to a narrow plane around Saturn's equator. The gravitational pull of Saturn's many moons helps to keep the particles in this plane, preventing them from spreading out into a thicker disk. The study of Saturn's rings has been greatly enhanced by the Cassini spacecraft, which orbited Saturn from 2004 to 2017. Cassini provided detailed images and data that have helped scientists to better understand the structure and dynamics of the rings. For example, Cassini discovered that the rings are not static but are constantly changing. Waves and ripples can be seen moving through the rings, caused by the gravitational influence of Saturn's moons. One of the most intriguing discoveries made by Cassini is the presence of propeller structures within the rings. These are caused by small moonlets that are embedded within the rings. As these moonlets orbit Saturn, they create disturbances in the surrounding ring particles, forming a shape that resembles a propeller. These structures provide a unique opportunity to study the interactions between small bodies and ring particles, offering insights into similar processes that may occur in other planetary systems. The rings of Saturn also play a crucial role in the planet's environment. They reflect sunlight, which helps to regulate the temperature of Saturn's upper atmosphere. Additionally, the rings are a source of material for Saturn's moons. As particles from the rings collide and coalesce, they can form new moons or add to the mass of existing ones. Saturn's rings are not only a scientific wonder, but also a source of inspiration and fascination for people around the world. Their beauty and complexity continue to captivate astronomers and laypeople alike, prompting us to ask questions about the nature of our solar system and the forces that shape it. What secrets do Saturn's rings still hold? How do they compare to the ring systems of other planets, such as Jupiter, Uranus, and Neptune? And what can they tell us about the history and evolution of our solar system? As we continue to explore and study Saturn and its rings, we are reminded of the vastness and complexity of the universe. Each new discovery brings us closer to understanding the intricate dance of celestial bodies that make up our solar system. Saturn's majestic rings are a testament to the beauty and wonder of the cosmos, inviting us to look up and ponder the mysteries of the universe. We delved into the captivating world of Saturn's rings, exploring their composition and the mysteries surrounding their origin. Saturn, with its stunning ring system, has long fascinated astronomers and the general public alike. The rings are primarily composed of ice particles, with a smaller amount of rocky debris and dust. These particles range in size from tiny grains to objects as large as mountains. The origin of Saturn's rings has been a topic of much debate, with theories suggesting they could be remnants of a destroyed moon or material left over from the planet's formation. Understanding these rings not only gives us insight into Saturn itself, but also into the processes that shape planetary systems. We shift our focus to another intriguing member of our solar system, Uranus, often referred to as the sideways planet. But what makes Uranus so unique, and why is it called the sideways planet? Let's dive into the fascinating characteristics of this ice giant and uncover the reasons behind its unusual orientation. Uranus is the seventh planet from the Sun and is classified as an ice giant, along with its neighbor Neptune. Unlike the gas giants Jupiter and Saturn, which are primarily composed of hydrogen and helium, Uranus has a significant amount of water, ammonia, and methane ice in its composition. This gives Uranus its distinct blue-green color, as the methane in its atmosphere absorbs red light and reflects blue light. However, what truly sets Uranus apart from the other planets in our solar system is its extreme axial tilt. Uranus's axis is tilted by about 98 degrees relative to its orbit around the Sun. This means that Uranus essentially rolls on its side as it orbits the Sun, with its poles facing the Sun at different times during its orbit. This is in stark contrast to most other planets, which have relatively small axial tilts and rotate more upright. But how did Uranus end up with such a peculiar tilt? One prevailing theory suggests that during the early formation of the solar system, Uranus experienced a massive collision with an Earth-sized object. This impact could have knocked the planet onto its side, resulting in the extreme tilt we observe today. This theory is supported by computer simulations and models that show how such an impact could have affected Uranus' rotation. The consequences of this tilt are profound. For one, it leads to extreme seasonal variations on Uranus. Each pole gets around 42 years of continuous sunlight, followed by 42 years of darkness. This results in unique atmospheric dynamics and weather patterns that are still not fully understood. The planet's unusual rotation also affects its magnetic field, which is tilted at a different angle than its rotational axis and is offset from the planet's center. This creates a complex and dynamic magnetic environment around Uranus. Uranus' sideways orientation also influences its ring system and moons. Like Saturn, Uranus has a set of rings, although they are much fainter and less extensive. The rings are composed of dark particles, which makes them difficult to observe from Earth. The planet's moons, of which there are 27 known, also orbit in the same tilted plane as the planet's equator. This alignment suggests that the moons and rings formed from the same disk of material that was affected by the event that tilted Uranus. The exploration of Uranus has been limited, with the most significant data coming from the Voyager 2 spacecraft, which flew by the planet in 1986. Voyager 2 provided valuable information about Uranus' atmosphere, rings, and moons, but much remains to be discovered. The planet's distance from Earth and the challenges of sending spacecraft to such a remote location have limited our ability to study it in detail. Despite these challenges, Uranus remains a subject of great interest for astronomers and planetary scientists. Its unique characteristics offer a window into the processes that can shape planetary bodies and their systems. Understanding Uranus' tilt and its effects could provide insights into similar phenomena in exoplanetary systems, where planets may also have unusual orientations. As we continue to explore the solar system and beyond, Uranus serves as a reminder of the diversity and complexity of planetary systems. Its sideways rotation challenges our understanding of planetary dynamics and invites us to question how such systems form and evolve. What other mysteries does Uranus hold, and what can it teach us about the universe? These questions drive the ongoing quest for knowledge and exploration. In conclusion, Uranus' title as the sideways planet is well-deserved, given its extreme axial tilt and the resulting unique characteristics. From its unusual seasons to its complex magnetic field, Uranus presents a fascinating case study in planetary science. As we look to the future, the potential for new missions to Uranus holds the promise of unlocking more secrets of this enigmatic ice giant. What new discoveries await us in the depths of the solar system? Only time and continued exploration will tell. we delved into the fascinating characteristics of Uranus, particularly its unusual sideways rotation. This ice giant stands out in our solar system due to its extreme axial tilt, which causes it to rotate almost on its side. This unique feature leads to unusual seasonal variations and has intrigued scientists for years. By understanding Uranus's tilt, we gain insights into the dynamic processes that can occur in planetary systems. Our focus shifts to Neptune, the eighth and farthest known planet from the Sun in our solar system. Neptune is often referred to as the blue giant due to its striking azure appearance, which is a result of methane in its atmosphere absorbing red light and reflecting blue. But beyond its captivating color, Neptune harbors some of the most intense and mysterious weather phenomena observed in our solar system: the dark spots. These dark spots are massive storm systems, akin to Jupiter's Great Red Spot, but with their own unique characteristics. Neptune's dark spots are transient features, appearing and disappearing over the course of a few years, unlike Jupiter's storm, which has persisted for centuries. What causes these dark spots to form and dissipate so rapidly? This is one of the many questions that scientists are eager to answer. The most famous of these storms is the Great Dark Spot, which was first observed by the Voyager 2 spacecraft during its flyby in 1989. This storm was nearly the size of Earth and was accompanied by white clouds of methane ice crystals, similar to cirrus clouds on Earth. However, when the Hubble Space Telescope observed Neptune in 1994, the Great Dark Spot had vanished, only to be replaced by a new storm in the planet's northern hemisphere. This rapid change puzzled scientists and highlighted the dynamic nature of Neptune's atmosphere. What drives these massive storms on Neptune? The planet's atmosphere is composed primarily of hydrogen, helium, and methane, with trace amounts of other gases. The extreme winds on Neptune, which can reach speeds of up to 1,500 miles per hour, are the fastest in the solar system. These winds are thought to play a crucial role in the formation and evolution of the dark spots. But why are these winds so powerful, and what sustains them in the absence of a significant internal heat source? One hypothesis suggests that Neptune's internal heat, though not as intense as Jupiter's, still contributes to the planet's weather systems. Neptune emits more energy than it receives from the Sun, indicating that there is some internal heat source at play. This heat could drive convection currents in the atmosphere, leading to the formation of storms. Additionally, the rapid rotation of Neptune, which completes a rotation in just about 16 hours, may also contribute to the extreme weather patterns by influencing atmospheric dynamics. Another intriguing aspect of Neptune's dark spots is their color. While they appear dark against the bright blue background of the planet, the exact composition and nature of these spots remain unclear. Some scientists speculate that the dark color could be due to a different composition of gases or aerosols within the storm systems, or perhaps a deeper layer of the atmosphere being exposed. Understanding the composition of these spots could provide valuable insights into the chemical processes occurring in Neptune's atmosphere. The transient nature of Neptune's dark spots also raises questions about the longevity and stability of such storm systems. Why do they appear and disappear so quickly compared to the long-lived storms on Jupiter? Are there underlying atmospheric conditions that favor the formation of these spots at certain times or locations on the planet? These questions remain at the forefront of planetary science research. In recent years, advancements in telescope technology and observational techniques have allowed scientists to study Neptune's atmosphere in greater detail from Earth. The Hubble Space Telescope continues to monitor the planet, providing valuable data on the evolution of its weather systems. Additionally, ground-based observatories equipped with adaptive optics have improved our ability to observe Neptune's dynamic atmosphere, offering new opportunities to study these enigmatic storms. As we continue to explore Neptune's dark spots, we are reminded of the complexity and diversity of planetary weather systems. Each planet in our solar system offers a unique laboratory for studying atmospheric dynamics, and Neptune is no exception. By unraveling the mysteries of its dark spots, We not only gain a deeper understanding of this distant world, but also enhance our knowledge of atmospheric processes that may occur on exoplanets beyond our solar system. In conclusion, Neptune's dark spots represent one of the many intriguing phenomena that make our solar system a rich tapestry of scientific discovery. As we probe deeper into the nature of these storms, we are challenged to rethink our understanding of planetary atmospheres and the forces that shape them. What new discoveries await us as we continue to observe and study Neptune? How might these findings inform our search for habitable worlds beyond our solar system? The journey of exploration and discovery continues, inviting us to look beyond the familiar and embrace the unknown. We delve into one of the most debated topics in the field of astronomy, the reclassification of Pluto from a planet to a dwarf planet. This decision, made by the International Astronomical Union (IAU) in 2006, sparked widespread discussion and controversy, both within the scientific community and among the general public. But what led to this significant change in Pluto's status, and why did it cause such an uproar? To understand the controversy, we must first explore what defines a planet. Prior to 2006, the definition of a planet was somewhat informal and based on historical and observational criteria. Pluto, discovered in 1930 by Clyde Tombaugh, was initially classified as the ninth planet in our solar system. For over 75 years, it held this status, orbiting the Sun beyond Neptune in a region known as the Kuiper Belt, which is populated with many icy bodies and remnants from the solar system's formation. However, as technology advanced and astronomers began discovering more celestial bodies in the Kuiper Belt, questions arose about what truly constitutes a planet. In particular, the discovery of Eris in 2005, a trans-Neptunian object that is similar in size to Pluto, challenged the traditional planetary lineup. If Pluto was considered a planet, should Eris and other similar objects also be classified as planets? This question prompted the IAU to reconsider the criteria for planetary classification. In 2006, during the IAU's 26th General Assembly in Prague, a new definition of a planet was proposed and voted upon. According to this new definition, for a celestial body to be considered a planet, it must meet three criteria. It must orbit the Sun, it must be spherical in shape due to its own gravity, and it must have cleared the neighborhood around its orbit. This third criterion means that the body must be gravitationally dominant in its orbital zone, having removed debris and smaller objects from its path. Pluto meets the first two criteria. It orbits the Sun and is spherical in shape. However, it does not meet the third criterion, as it shares its orbital zone with other objects in the Kuiper Belt. As a result, Pluto was reclassified as a dwarf planet, a new category created to accommodate celestial bodies that meet the first two criteria but not the third. The decision to demote Pluto was not without its critics. Many astronomers and members of the public felt a sentimental attachment to Pluto as the ninth planet, and the reclassification was seen by some as an unnecessary change. Others argued that the new definition of a planet was too restrictive and excluded other celestial bodies that deserved recognition as planets. Despite the controversy, the reclassification of Pluto has had significant implications for our understanding of the solar system. It has prompted astronomers to explore and study the Kuiper Belt more extensively, leading to the discovery of numerous other dwarf planets and trans-Neptunian objects. This has expanded our knowledge of the solar system's structure and the diversity of objects within it. The debate over Pluto's status also highlights the evolving nature of scientific knowledge. As new discoveries are made and our understanding of the universe grows, definitions and classifications must be revisited and revised. This process is a fundamental aspect of scientific inquiry and progress. So, what does the future hold for Pluto and other celestial bodies in the Kuiper Belt? Will new discoveries prompt further changes to planetary classifications? And how will our understanding of the solar system continue to evolve as we explore beyond our current boundaries? These questions remain open for exploration and discussion, inviting us to consider the dynamic and ever-changing nature of the cosmos. In conclusion, Pluto's demotion is not just a story about a celestial body losing its planetary status. It is a reflection of the complexities and challenges of scientific classification, the emotional connections we form with the cosmos, and the ongoing quest for knowledge and understanding in the vastness of space. As we continue to explore and learn, the story of Pluto serves as a reminder of the dynamic and ever-evolving nature of our universe. We delved into the fascinating and somewhat contentious topic of Pluto's reclassification. Once considered the ninth planet of our solar system, Pluto was redefined as a dwarf planet in 2006 by the International Astronomical Union (IAU). This decision was based on new criteria that a celestial body must meet to be classified as a planet. Specifically, a planet must orbit the Sun, be spherical in shape due to its own gravity, and have cleared its orbit of other debris. Pluto met the first two criteria but failed the third, as it shares its orbital zone with other objects in the Kuiper Belt. This reclassification sparked debates and discussions within the scientific community and among the public, highlighting how our understanding of the cosmos is ever-evolving. We shift our focus from the icy realms of the Kuiper Belt to another set of fascinating celestial objects, comets. Often referred to as cosmic wanderers, comets are icy bodies that travel through our solar system, offering a glimpse into its early history. But what exactly are comets, and why did they capture our imagination? Comets are composed of ice, dust, and rocky material. They originate from the outer regions of the solar system, primarily from two areas, the Kuiper Belt and the Oort cloud. The Kuiper Belt, as mentioned earlier, is a region beyond Neptune filled with icy bodies, while the Oort cloud is a hypothetical distant spherical shell surrounding the solar system. Comets from the Kuiper Belt are known as short-period comets, taking less than 200 years to orbit the Sun, whereas those from the Oort cloud are long-period comets, with orbits that can last thousands of years. When a comet approaches the Sun, the heat causes its ice to vaporize, creating a glowing coma or a cloud of gas and dust around its nucleus. This process also forms a tail that always points away from the Sun due to the solar wind. The tail can stretch for millions of kilometers, creating a spectacular sight in the night sky. Have you ever wondered why comets have two tails? One is made of gas and ions and the other of dust particles, each reacting differently to the Sun's radiation and solar wind. Comets have been observed for centuries and have often been considered omens or harbingers of change. Historical records show that ancient civilizations, such as the Chinese, Babylonians, and Greeks, meticulously documented comet appearances. One of the most famous comets is Halley's Comet, named after Edmund Halley, who correctly predicted its return in 1758. Halley's Comet is a short-period comet visible from Earth approximately every 76 years, with its next appearance expected in 2061. What stories and myths have you heard about comets? In addition to their cultural significance, comets are scientifically valuable. They are considered time capsules from the early solar system, containing materials that have remained largely unchanged for billions of years. By studying comets, scientists can gain insights into the conditions and processes that existed when the solar system was forming. Space missions, such as the European Space Agency's Rosetta, which studied Comet 67P/Churyumov-Gerasimenko, have provided valuable data about the composition and behavior of comets. What secrets do you think these cosmic wanderers hold about the origins of our solar system? Comets also play a role in the theory of panspermia, which suggests that life on Earth may have been seeded by organic compounds delivered by comets and asteroids. This theory is supported by the discovery of complex organic molecules, such as amino acids, on comets. Could comets be the key to understanding the origins of life on Earth? As we continue to explore and study these fascinating objects, comets remind us of the dynamic and interconnected nature of our solar system. They serve as a bridge between the past and the present, offering clues about the formation and evolution of our cosmic neighborhood. What future discoveries about comets do you think will reshape our understanding of the universe? In conclusion, comets, with their icy compositions and dramatic appearances, are truly the cosmic wanderers of our solar system. From their origins in the distant reaches of the Kuiper Belt and Oort cloud to their spectacular journeys around the sun, comets captivate our imagination and challenge our understanding of the cosmos. As we continue to study these celestial travelers, we are reminded of the vastness and complexity of the universe and our place within it. What mysteries of the cosmos will comets help us unravel next? We explored the fascinating journey of comets, those icy wanderers that travel through our solar system. We delved into their origins, composition, and the spectacular displays they create as they approach the sun. We learned how these celestial bodies, composed of ice, dust, and rocky material, originate from the distant regions of our solar system, such as the Kuiper Belt and the Oort cloud. As they travel closer to the sun, the heat causes their icy surfaces to vaporize, creating a glowing coma and a tail that can stretch for millions of kilometers. These tails always point away from the sun due to the solar wind, a concept that leads us directly into our current act. We shift our focus to the sun itself and its profound influence on space weather through the phenomenon known as solar winds. But what exactly are solar winds, and how do they affect our solar system? Let's dive in to uncover the mysteries of this powerful force. The sun, our closest star, is a massive ball of hot plasma, primarily composed of hydrogen and helium. It is constantly undergoing nuclear fusion in its core, where hydrogen atoms are fused into helium, releasing an immense amount of energy. This energy radiates outward, eventually reaching the sun's outer layer, the corona. The corona is not only incredibly hot, but also the source of solar winds. Solar winds are streams of charged particles, primarily electrons and protons, that are ejected from the sun's corona. These particles travel through space at speeds ranging from 300 to 800 kilometers per second. But what causes these particles to be released from the sun in the first place? The answer lies in the sun's magnetic field. The sun's magnetic field is complex and dynamic, with magnetic lines of force that twist and turn due to the sun's rotation and the movement of plasma within it. Occasionally, these magnetic lines can become so twisted that they snap, releasing energy and charged particles into space. This process is known as magnetic reconnection and is a key driver of solar winds. Once released, solar winds travel throughout the solar system, influencing the space environment around planets, moons, and other celestial bodies. But how exactly do these winds impact our solar system? One of the most significant effects of solar winds is their interaction with planetary magnetic fields, particularly Earth's. Earth is surrounded by a magnetic field known as the magnetosphere, which acts as a protective shield against solar winds. When solar winds encounter Earth's magnetosphere, they can cause a variety of phenomena, including geomagnetic storms and auroras. Geomagnetic storms occur when solar winds disturb the magnetosphere, leading to fluctuations in Earth's magnetic field. These storms can have significant effects on technology, such as disrupting satellite communications and power grids. Auroras, on the other hand, are beautiful natural light displays that occur when charged particles from solar winds collide with gases in Earth's atmosphere. These collisions excite the gases, causing them to emit light in various colors, creating the stunning displays known as the northern and southern lights. But Earth's magnetosphere isn't the only region affected by solar winds. These winds also interact with the heliosphere, the vast bubble-like region of space dominated by the sun's magnetic field and solar wind. The heliosphere acts as a protective barrier, shielding the solar system from cosmic rays and interstellar material. However, the boundary of the heliosphere, known as the heliopause, is constantly changing due to variations in solar wind pressure. Solar winds also play a crucial role in shaping the tails of comets, as we learned in Act 12. As a comet approaches the sun, the solar wind blows its ionized gases away from the sun, forming a tail that always points in the opposite direction. This interaction between solar winds and comets provides valuable insights into the composition and behavior of both the winds and the comets themselves. Furthermore, solar winds are responsible for the creation of the solar wind termination shock, a boundary where the solar wind slows down abruptly due to interactions with the interstellar medium. This boundary marks the beginning of the outer heliosphere and is a region of great interest to scientists studying the sun's influence on the solar system. Understanding solar winds is not only crucial for comprehending space weather, but also for the future of space exploration. As humanity ventures further into space, understanding and predicting solar wind behavior will be essential for the safety of astronauts and the success of space missions. For instance, solar winds can pose a radiation hazard to astronauts traveling beyond Earth's protective magnetosphere, making it vital to develop strategies to mitigate these risks. In conclusion, solar winds are a powerful and dynamic force that shapes the environment of our solar system. From influencing planetary magnetospheres to creating stunning auroras and shaping comet tails, the impact of solar winds is far-reaching. As we continue to study and understand this phenomenon, we gain valuable insights into the sun's influence on space weather and the broader cosmos. What new discoveries will we make about solar winds in the future, and how will they shape our understanding of the universe? The journey of exploration continues, and the answers await us in the vast expanse of space. We delved into the fascinating and dynamic influence of the sun on space weather. We explored how solar winds, streams of charged particles emitted by the sun, travel through space and interact with planetary atmospheres, magnetic fields, and even technological systems on Earth. This understanding is crucial as it helps us predict and mitigate the effects of solar storms, which can disrupt satellites, power grids, and communication systems. The sun, being the center of our solar system, plays a pivotal role in shaping the space environment, and understanding its behavior is key to safeguarding our technological infrastructure and enhancing our knowledge of space weather phenomena. Now we shift our focus from the sun's immediate influence to a distant and intriguing region of our solar system. The Kuiper Belt is a vast expanse located beyond the orbit of Neptune, filled with icy bodies and remnants from the early solar system. This region is of particular interest to astronomers and scientists because it holds clues to the formation and evolution of our solar system. But what exactly is the Kuiper Belt, and why is it so important? The Kuiper Belt is a circumstellar disk in the outer solar system, extending from about 30 to 55 astronomical units, AU, from the Sun. To put this into perspective, 1 astronomical unit is the average distance from the Earth to the Sun, approximately 93 million miles or 150 million kilometers. This means the Kuiper Belt is located far beyond the orbit of the outermost planet Neptune, making it a region that is both remote and challenging to study. One of the most well-known objects in the Kuiper Belt is Pluto, which was once considered the 9th planet of our solar system before being reclassified as a dwarf planet. Pluto's reclassification in 2006 by the International Astronomical Union, IAU, was partly due to the discovery of other similar-sized objects in the Kuiper Belt, which raised questions about what constitutes a planet. This decision sparked debates and discussions in the scientific community and the public, highlighting the complexities of defining celestial bodies. The Kuiper Belt is home to a diverse array of objects, collectively known as Kuiper Belt objects, KBOs. These objects range in size from small icy bodies to larger dwarf planets like Pluto and Eris. The composition of these objects is primarily ice and rock, and they are believed to be remnants from the early solar system that never coalesced into a planet. Studying these objects provides valuable insights into the conditions and processes that existed during the solar system's formation. One of the key missions that have provided significant information about the Kuiper Belt is NASA's New Horizons mission. Launched in 2006, New Horizons made a historic flyby of Pluto in 2015, capturing detailed images and data that transformed our understanding of this distant world. Following its encounter with Pluto, New Horizons continued its journey into the Kuiper Belt, conducting a flyby of another KBO, Aerokoth, formerly known as Ultima Thule, in 2019. These missions have offered unprecedented glimpses into the characteristics and composition of Kuiper Belt objects, revealing complex surfaces, varied geology, and unexpected features. The study of the Kuiper Belt is not only about understanding these distant icy bodies, but also about piecing together the history of our solar system. The Kuiper Belt is thought to be a remnant of the primordial disk from which the planets formed. By examining the composition and distribution of KBOs, scientists can infer the processes that shaped the early solar system and led to the formation of planets. Moreover, the Kuiper Belt is believed to be the source of many short-period comets that occasionally visit the inner solar system, providing further connections between this distant region and the more familiar parts of our solar system. The exploration of the Kuiper Belt also raises intriguing questions about the potential for similar regions around other stars. If our solar system has a Kuiper Belt, could other star systems have their own versions of this icy region? The study of exoplanets and their surrounding environments is an exciting and rapidly evolving field, and the insights gained from the Kuiper Belt could inform our understanding of planetary systems beyond our own. As we continue to explore the Kuiper Belt, new discoveries and questions are sure to emerge. What other objects lie hidden in this distant region? How do the characteristics of KBOs vary, and what can they tell us about the conditions in the early solar system? The Kuiper Belt remains a frontier of exploration, offering a window into the past and a pathway to understanding the broader cosmos. In conclusion, the Kuiper Belt invites us to journey beyond the familiar planets and delve into a region filled with icy relics from the dawn of our solar system. As we uncover the secrets of the Kuiper Belt, we not only enhance our knowledge of this distant region, but also gain a deeper appreciation for the complexity and diversity of our solar system. The Kuiper Belt is a testament to the enduring mysteries of space, reminding us that there is still much to discover and learn as we continue our exploration of the cosmos. As we transition from the icy expanses of the Kuiper Belt, our cosmic journey brings us closer to home, yet still far from Earth, to the largest planet in our solar system, Jupiter. Known for its massive size and distinctive bands of clouds, Jupiter is not only a giant in terms of its physical dimensions, but also in terms of its gravitational influence and its retinue of moons. This act delves into the fascinating world of Jupiter's moons, each with its own unique characteristics and mysteries. Jupiter is orbited by a staggering number of moons, with current counts exceeding 79. These moons vary greatly in size, composition, and geological activity, making them a subject of immense interest for astronomers and planetary scientists. The four largest and most well-known of these moons are the Galilean moons, Io, Europa, Ganymede, and Callisto. Discovered by Galileo Galilei in 1610, these moons were the first objects found to orbit another planet, challenging the geocentric model of the universe that prevailed at the time. Let's begin with Io, the innermost of the Galilean moons. Io is slightly larger than Earth's moon, and is the most geologically active body in the solar system. This moon is dotted with hundreds of volcanoes, some of which are active and spew sulfur and sulfur dioxide into space. The intense volcanic activity is a result of tidal heating, a process driven by the gravitational pull of Jupiter and the other Galilean moons. This constant flexing generates heat, melting Io's interior and fueling its volcanoes. The surface of Io is constantly being reshaped by lava flows, creating a colorful landscape of reds, yellows, and whites. Next, we have Europa, a moon that has captured the imagination of scientists and the public alike due to the possibility of an ocean beneath its icy crust. Europa's surface is one of the smoothest in the solar system, characterized by a layer of water ice crisscrossed by a network of cracks and ridges. Beneath this icy shell, it is believed that a vast ocean of liquid water exists, kept warm by the same tidal forces that heat Io. This subsurface ocean makes Europa a prime candidate in the search for extraterrestrial life. Could there be organisms thriving in the dark depths of Europa's ocean, similar to those found around hydrothermal vents on Earth? Moving outward, we encounter Ganymede, the largest moon in the solar system, even bigger than the planet Mercury. Ganymede is unique among moons as it possesses its own magnetic field, likely generated by a liquid iron or iron sulfide core. The surface of Ganymede is a mix of two types of terrain: highly cratered dark regions and lighter regions marked with grooves and ridges. These features suggest a complex geological history, possibly involving tectonic processes. Ganymede also harbors a subsurface ocean, adding to the intrigue of this massive moon. Finally, we reach Callisto, the outermost of the Galilean moons. Callisto is heavily cratered and is considered the most heavily cratered object in the solar system. Unlike its siblings, Callisto shows little evidence of geological activity, leading scientists to believe it has remained largely unchanged for billions of years. This ancient surface provides a window into the early solar system, preserving a record of impacts and other processes from that time. Despite its seemingly inactive nature, Callisto is also thought to have a subsurface ocean, making it another potential habitat for life. Beyond the Galilean moons, Jupiter is orbited by many smaller moons, each with its own story. These include the irregular moons, which are thought to be captured asteroids or fragments from collisions. Some of these moons, like Amalthea, are closer to Jupiter and are shaped by the planet's intense radiation and gravitational forces. Jupiter's moons offer a diverse array of environments and phenomena, making them a focal point for future exploration. Missions like NASA's Europa Clipper and the European Space Agency's JUICE, Jupiter Icy Moons Explorer, are set to explore these moons in greater detail, seeking to unlock their secrets and perhaps answer the age-old question of whether life exists beyond Earth. As we conclude our exploration of Jupiter's moons, we are left with a sense of wonder about the dynamic and varied nature of these celestial bodies. Each moon presents its own set of challenges and opportunities for discovery. What new insights will future missions bring? Could the exploration of these moons lead to groundbreaking discoveries about the potential for life elsewhere in the solar system? The moons of Jupiter continue to captivate our imagination, promising to reveal more about the mysteries of our cosmic neighborhood. We delved into the fascinating world of Jupiter's moons, exploring the diverse satellites that orbit the largest planet in our solar system. Jupiter, with its immense gravitational pull, hosts a variety of moons, each with unique characteristics and intriguing features. From the volcanic activity on Io to the icy surface of Europa, and the vast magnetic field interactions with Ganymede, Jupiter's moons offer a plethora of scientific interest and mysteries waiting to be unraveled. We shift our focus to Saturn's Titan, the only moon in our solar system with a thick atmosphere. Titan stands out among the many moons of Saturn due to its dense, nitrogen-rich atmosphere, which is reminiscent of early Earth. This atmosphere is primarily composed of nitrogen, with small amounts of methane and hydrogen, creating a complex and dynamic environment. Titan's atmosphere is not only thick but also hazy, obscuring the surface from view in visible light. This haze is caused by complex organic molecules known as tholins, which form in the upper atmosphere and gradually settle onto the surface. These tholins give Titan its characteristic orange hue and are of great interest to scientists studying prebiotic chemistry, as they may provide clues about the chemical processes that led to the development of life on Earth. One of the most intriguing aspects of Titan is its weather system, which includes methane rain and lakes. Unlike Earth, where water is the primary component of the hydrological cycle, Titan's cycle is based on methane and ethane. The moon experiences seasonal changes, with methane clouds forming and dissipating, and methane rain falling to create rivers and lakes on the surface. These lakes and seas, primarily composed of liquid methane and ethane, are concentrated near the polar regions and are a unique feature in our solar system. The surface of Titan is diverse and varied, with vast dune fields, icy plains, and rugged highlands. The dunes, primarily composed of hydrocarbon particles, are shaped by the winds in Titan's thick atmosphere. These dunes are similar in appearance to those found in Earth's deserts, yet they are formed from entirely different materials. The icy plains are believed to be composed of water ice, which behaves like rock at the frigid temperatures found on Titan. One of the most exciting discoveries about Titan is the presence of cryovolcanoes, which are volcanoes that erupt with substances like water, ammonia, or methane, rather than molten rock. These cryovolcanoes suggest that Titan may have a subsurface ocean, potentially harboring conditions suitable for life. The possibility of a liquid water ocean beneath Titan's icy crust makes it a prime target for astrobiological studies and future exploration missions. The exploration of Titan has been greatly advanced by the Cassini-Huygens mission, a collaborative effort between NASA, the European Space Agency, and the Italian Space Agency. Launched in 1997, the Cassini spacecraft spent 13 years studying Saturn and its moons, providing invaluable data about Titan's atmosphere, surface, and potential subsurface ocean. In 2005, the Huygens probe, carried by Cassini, successfully landed on Titan, marking the first landing on a moon in the outer solar system. The data collected by Huygens revealed a landscape shaped by erosion, with channels and valleys carved by liquid methane. Titan's potential for prebiotic chemistry and the possibility of a subsurface ocean make it a compelling target for future exploration. Scientists are eager to learn more about the moon's complex atmosphere, surface processes, and potential habitability. The Dragonfly mission, planned by NASA for the mid-2030s, aims to explore Titan's surface with a rotorcraft lander. This mission will investigate the chemical processes occurring on Titan and search for signs of prebiotic chemistry, providing further insights into the moon's potential for life. As we continue to explore Titan, we are reminded of the vast diversity and complexity of our solar system. Each moon and planet offers unique insights into the processes that have shaped our cosmic neighborhood. Titan, with its thick atmosphere and intriguing surface features, challenges our understanding of planetary science and astrobiology, inviting us to explore further and ask new questions about the potential for life beyond Earth. What mysteries will Titan reveal as we continue to explore its surface and atmosphere? How does its methane cycle compare to Earth's water cycle? And what can it teach us about the dynamics of planetary atmospheres? As we look to the future of space exploration, Titan stands as a beacon of scientific curiosity and discovery, inviting us to delve deeper into the unknown and expand our understanding of the universe. In Act 16, titled Saturn's Titan, we delved into the fascinating world of Titan, Saturn's largest moon and the only one in our solar system known to have a dense atmosphere. Titan's atmosphere is primarily composed of nitrogen, similar to Earth, but it also contains methane and hydrogen, which contribute to its thick, hazy appearance. This unique atmospheric composition has intrigued scientists for years, as it presents a rare opportunity to study weather patterns and surface conditions that may resemble those of early Earth. Titan's surface is equally captivating, with vast lakes and rivers of liquid methane and ethane, and a landscape sculpted by these hydrocarbon flows. The Cassini-Huygens mission provided invaluable data about Titan, revealing its complex weather systems, seasonal changes, and even the possibility of a subsurface ocean. This exploration of Titan raised numerous questions about the potential for life in such an alien environment and the processes that shape its intriguing landscape. We journey even further into the vast reaches of our solar system. The Oort cloud represents one of the most distant and mysterious regions, a hypothetical cloud of icy bodies that is believed to surround our solar system at a distance of up to 100,000 astronomical units, AU, from the Sun. But what exactly is the Oort cloud, and why is it so significant in our understanding of the solar system? The concept of the Oort cloud was first proposed by Dutch astronomer Jan Oort in 1950. He suggested its existence to explain the origins of long-period comets, which have orbits that can take them thousands of years to complete. These comets, unlike their short-period counterparts that originate from the Kuiper Belt, appear to come from a distant, spherical shell surrounding the solar system. The Oort cloud is thought to contain billions, if not trillions, of icy bodies, remnants from the early solar system that were scattered far from the sun by the gravitational interactions with the giant planets. One of the most intriguing aspects of the Oort cloud is its role as a reservoir for comets. When a comet from the Oort cloud is nudged by the gravitational influence of a passing star or the galactic tide, it can be sent hurtling towards the inner solar system, becoming visible as a bright, glowing object with a characteristic tail. These comets provide scientists with valuable information about the conditions and materials present in the early solar system, as they are composed of primordial ice and dust that have remained largely unchanged for billions of years. The Oort cloud is divided into two regions: the inner Oort cloud or Hills cloud, and the outer Oort cloud. The inner Oort cloud is thought to be more densely populated and lies closer to the sun, while the outer Oort cloud extends much farther into space. The boundary of the Oort cloud marks the edge of the sun's gravitational influence, beyond which lies interstellar space. This boundary is known as the heliopause, where the solar wind from the sun slows down and merges with the interstellar medium. Exploring the Oort cloud presents significant challenges due to its immense distance and the sparse distribution of its objects. To date, no spacecraft has visited the Oort cloud, and its existence remains theoretical, supported by indirect evidence from the study of long-period comets. However, understanding the Oort cloud is crucial for piecing together the history of our solar system and the processes that led to its formation. The study of the Oort cloud also raises intriguing questions about the potential for similar structures around other stars. If the Oort cloud is a common feature of planetary systems, it could have implications for our understanding of cometary impacts on planets, including Earth, and their role in delivering water and organic materials that may have contributed to the development of life. As we venture into the outer edges of our solar system, the Oort cloud stands as a testament to the vastness and complexity of the cosmos. It challenges our perceptions of distance and time, and invites us to consider the dynamic processes that continue to shape our solar system. What secrets does the Oort cloud hold, and how might they change our understanding of the universe? The answers to these questions await future explorations and discoveries, as humanity continues its quest to unravel the mysteries of the cosmos. We journey to the farthest reaches of our solar system, exploring the mysterious Oort cloud. This vast spherical shell of icy objects surrounds our solar system and is believed to be the source of long-period comets. It represents the boundary between the gravitational influence of our sun and the interstellar space beyond. The Oort cloud is a fascinating region that challenges our understanding of the solar system's formation and evolution, as it contains remnants from the early solar system. We delved into its composition, its role in the solar system, and the scientific methods used to study it despite its immense distance from Earth. We shift our focus back to a phenomenon that occurs much closer to home: solar eclipses. A solar eclipse is a celestial event that captures the imagination of people across the globe. But what exactly happens during a solar eclipse, and why do they occur? A solar eclipse takes place when the moon passes between the Earth and the sun, blocking all or part of the sun's light. This alignment of the sun, moon, and Earth is a rare occurrence, and it can only happen during a new moon when the moon is directly between the Earth and the sun. But why don't we experience a solar eclipse every month during the new moon? The answer lies in the moon's orbit. The moon's orbit around Earth is tilted about 5 degrees relative to Earth's orbit around the sun. This means that during most new moons, the moon is either above or below the plane of Earth's orbit, and thus it does not block the sun's light. A solar eclipse can only occur when the new moon is near one of the 2 points in its orbit where it crosses the plane of Earth's orbit, known as nodes. When this alignment happens, the moon casts a shadow on Earth, leading to a solar eclipse. There are 3 main types of solar eclipses: total, partial, and annular. A total solar eclipse occurs when the moon completely covers the sun, as seen from Earth. This happens when the moon is close enough to Earth in its orbit to appear larger than the sun in the sky. During a total eclipse, the day briefly turns to night and the sun's corona, its outer atmosphere, becomes visible. This is a breathtaking sight that has fascinated humanity for centuries. A partial solar eclipse occurs when only a part of the sun is obscured by the moon. During a partial eclipse, the alignment of the sun, moon, and earth is such that the moon only partially covers the sun, resulting in a crescent-shaped sun. This type of eclipse is more common than a total eclipse and can be seen over a larger area. An annular solar eclipse occurs when the moon is too far from Earth to completely cover the sun. In this case, the moon appears smaller than the sun, and a ring of the sun's surface, known as the Ring of Fire, remains visible around the moon. Annular eclipses are also known as ring eclipses and are a spectacular sight. The path of totality is the narrow path on Earth's surface where a total solar eclipse is visible. This path is usually only about 100 miles wide, and it moves across the Earth as the moon's shadow travels from west to east. Observers outside this path will see a partial eclipse. The duration of totality, when the sun is completely covered, can last up to about 7 minutes, but most total eclipses last only a few minutes. Solar eclipses have been observed and recorded by humans for thousands of years. Ancient civilizations often viewed them as omens or messages from the gods. Today, we understand the scientific principles behind eclipses, and they provide valuable opportunities for scientific research. During a total solar eclipse, scientists can study the sun's corona, which is usually hidden by the bright light of the sun's surface. Eclipses also allow for experiments in gravitational physics and help improve our understanding of the dynamics of the Earth-Moon-Sun system. Safety is a crucial consideration when observing a solar eclipse. Looking directly at the sun without proper eye protection can cause serious eye damage or even blindness. Special eclipse glasses or viewers are necessary to safely observe the sun during an eclipse. Alternatively, a pinhole projector can be used to project an image of the sun onto a surface for safe viewing. The next total solar eclipse visible from the United States will occur on April 8, 2024. This event will provide a unique opportunity for millions of people to experience the wonder of a total solar eclipse. As we anticipate this celestial event, it's worth reflecting on the intricate dance of celestial bodies that make solar eclipses possible. How does the precise alignment of the sun, moon, and earth create such a spectacular phenomenon? What can we learn from observing these rare events? And how do solar eclipses continue to inspire awe and curiosity in people around the world? In conclusion, solar eclipses are a testament to the beauty and complexity of our solar system. They remind us of the interconnectedness of celestial bodies and the delicate balance that governs their movements. As we continue to study and appreciate these awe-inspiring events, we gain a deeper understanding of the universe and our place within it. Whether you're a seasoned astronomer or a curious observer, the experience of witnessing a solar eclipse is one that leaves a lasting impression, sparking wonder and curiosity about the cosmos. We delved into the fascinating phenomenon of solar eclipses, where the alignment of the sun, moon, and earth creates a spectacular celestial event. We'd explored how these alignments occur and the different types of solar eclipses, such as total, partial, and annular eclipses. By understanding the positions of these celestial bodies, we gained insight into why solar eclipses happen and how they vary depending on the observer's location on Earth. We turn our attention to another fundamental aspect of our planet's interaction with the sun, the seasons. Have you ever wondered why we experience different seasons throughout the year? Why is it that while one hemisphere basks in the warmth of summer, the other shivers in the chill of winter? The answer lies in the Earth's tilted axis and its orbit around the sun. The Earth's axis is an imaginary line that runs from the North Pole to the South Pole. This axis is tilted at an angle of approximately 23.5 degrees relative to its orbit around the sun. This tilt is crucial in creating the seasons. But how exactly does this tilt affect the Earth's climate and weather patterns? As the Earth orbits the sun, the tilt of its axis causes different parts of the Earth to receive varying amounts of sunlight throughout the year. This variation in sunlight is what leads to the changing seasons. Let's break it down further. During the course of a year, the Earth's orbit around the sun is elliptical, meaning it is not a perfect circle. As a result, the distance between the Earth and the sun changes slightly over the year. However, this distance variation is not the primary reason for the seasons. The key factor is the axial tilt. When the northern hemisphere is tilted towards the sun, it experiences summer. This is because the sun's rays strike this part of the Earth more directly, resulting in longer days and shorter nights. The increased sunlight and longer days lead to warmer temperatures. Conversely, during this time, the southern hemisphere is tilted away from the sun, experiencing winter with shorter days and longer nights. 6 months later, the situation reverses. The southern hemisphere is now tilted towards the sun, enjoying the warmth of summer, while the northern hemisphere is tilted away, experiencing the cold of winter. This cyclical pattern of changing sunlight and temperature is what defines the seasons. The equinoxes and solstices are key markers in this cycle. The equinoxes occur twice a year, around March 21st and September 23rd, when the tilt of the Earth's axis is such that the sun is directly above the equator. On these days, day and night are approximately equal in length. The March equinox marks the beginning of spring in the northern hemisphere and autumn in the southern hemisphere, while the September equinox marks the start of autumn in the northern hemisphere and spring in the southern hemisphere. The solstices, on the other hand, occur around June 21st and December 21st. During the June solstice, the northern hemisphere is tilted towards the sun, resulting in the longest day of the year and the official start of summer. Conversely, the December solstice marks the shortest day of the year in the northern hemisphere and the beginning of winter. In the southern hemisphere, these dates are reversed, with the June solstice marking the start of winter and the December solstice the beginning of summer. But why is the Earth's axis tilted in the first place? Scientists believe that this tilt was caused by a massive collision with a Mars-sized body early in Earth's history. This impact not only tilted the Earth's axis, but also led to the formation of the Moon. The tilt has remained relatively stable over millions of years, thanks to the gravitational influence of the Moon, which helps to stabilize the Earth's axial tilt. The tilt of the Earth's axis is not only responsible for the seasons, but also affects the climate and weather patterns across the globe. Regions near the equator, where the sun's rays are more direct year-round, experience little variation in temperature and have tropical climates. In contrast, regions closer to the poles experience more extreme variations in temperature and have polar or temperate climates. Understanding the Earth's tilted axis and its effects on the seasons helps us appreciate the intricate balance of our planet's climate system. It also highlights the interconnectedness of celestial mechanics and life on Earth. As we continue to study and observe these natural phenomena, we gain a deeper understanding of our place in the universe. So, the next time you experience a change in season, take a moment to consider the remarkable journey of our planet around the sun and the role of its tilted axis in shaping the world we live in. How does this knowledge change your perspective on the seasons? What other natural phenomena might be influenced by the Earth's axial tilt? As we ponder these questions, we continue our exploration of the wonders of our solar system and beyond. We delved into the fascinating concept of Earth's tilted axis and its profound effects on our planet. We explored how this tilt is responsible for the changing seasons, influencing everything from weather patterns to the length of daylight hours. Understanding Earth's axial tilt helped us appreciate the delicate balance that governs our planet's climate and the cyclical nature of seasons. We shift our focus from Earth to the broader cosmic dance of planetary orbits. This act is dedicated to unraveling the mysteries of planetary motion through the lens of Kepler's laws. These laws, formulated by the German mathematician and astronomer Johannes Kepler in the early 17th century, revolutionized our understanding of how planets move around the sun. Kepler's laws of planetary motion are a set of 3 scientific principles that describe the motion of planets in our solar system. But what exactly are these laws, and why are they so important? Let's embark on this journey to uncover the secrets of planetary orbits. Kepler's first law, often referred to as the law of ellipses, states that the orbit of a planet around the sun is an ellipse, with the sun at one of the two foci. This was a groundbreaking revelation at the time, as it contradicted the long-held belief that planetary orbits were perfect circles. An ellipse is an elongated circle, and the fact that planets travel in elliptical paths means that their distance from the sun varies throughout their orbit. This law helps explain why planets sometimes appear closer to the sun and at other times farther away. Kepler's second law, known as the law of equal areas, describes the speed at which a planet travels along its elliptical orbit. According to this law, a line segment joining a planet and the sun sweeps out equal areas during equal intervals of time. This means that a planet moves faster when it is closer to the sun and slower when it is farther away. This variation in speed is due to the gravitational pull of the sun, which is stronger when a planet is nearer and weaker when it is farther. Kepler's third law, the law of harmonies, provides a relationship between the time a planet takes to orbit the sun and its average distance from the sun. Specifically, the square of a planet's orbital period, the time it takes to complete one orbit, is proportional to the Q of its average distance from the sun. This law allows us to compare the motion of different planets and understand the harmony of their orbits within the solar system. These laws not only describe the motion of planets in our solar system, but also laid the groundwork for Isaac Newton's theory of universal gravitation. Kepler's insights helped Newton formulate his laws of motion and the law of gravitation, which further explained why planets move in the way Kepler described. But how did Kepler arrive at these laws? His journey was not an easy one. Kepler worked with the precise astronomical observations of Tycho Brahe, a renowned Danish astronomer. By meticulously analyzing Brahe's data, Kepler was able to identify patterns and relationships that led to the formulation of his laws. His work marked a significant shift from the geocentric model of the universe, which placed Earth at the center, to the heliocentric model, where the sun is at the center of the solar system. Kepler's laws have far-reaching implications beyond our solar system. They apply to any celestial body orbiting another, such as moons orbiting planets or exoplanets orbiting distant stars. These laws are fundamental to the field of astronomy and are used to predict the motion of celestial bodies, design spacecraft trajectories, and even search for new planets. As we continue to explore the universe, Kepler's laws remain a cornerstone of our understanding of planetary motion. They remind us of the elegance and simplicity of the natural laws that govern the cosmos. So, as we gaze up at the night sky, we can appreciate the intricate dance of planets and stars, all moving in harmony according to the principles laid down by Johannes Kepler centuries ago. In the next act, we will delve deeper into the implications of these laws and explore how they have shaped our understanding of the universe. How did these laws help us in modern astronomy? What are the limitations of Kepler's laws, and how have they been refined over time? Join us as we continue to unravel the mysteries of the cosmos and discover the wonders of planetary motion. We delve into the fascinating world of solar flares and their significant impact on Earth. But what exactly are solar flares, and why do they matter to us? Let's explore these questions and uncover the intriguing dynamics of space weather. Solar flares are sudden and intense bursts of radiation emanating from the sun's surface. They occur when magnetic energy that has built up in the solar atmosphere is suddenly released. This release of energy results in a burst of electromagnetic radiation across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. But how did these solar flares form, and what triggers them? The sun is a massive ball of hot plasma, with its surface and atmosphere teeming with magnetic activity. The sun's magnetic field is complex and dynamic, constantly changing and evolving. This magnetic field is generated by the movement of electrically charged particles within the sun. Sometimes, the magnetic field lines become twisted and tangled, storing a tremendous amount of energy. When these magnetic field lines snap and reconnect, a solar flare is produced. Now, you might be wondering, how did these solar flares affect Earth? Although the sun is approximately 93 million miles away, solar flares can have a profound impact on our planet. When a solar flare occurs, it releases a burst of energy that travels through space at the speed of light. This energy can reach Earth in just over 8 minutes, affecting our planet's magnetic field and atmosphere. One of the most immediate effects of solar flares on Earth is the disruption of radio communications. The high-energy radiation from a solar flare can ionize the Earth's upper atmosphere, particularly the ionosphere, which is crucial for radio wave propagation. This ionization can lead to radio blackouts, affecting communication systems that rely on high-frequency radio waves, such as aviation and maritime operations. But the impact of solar flares doesn't stop there. They can also pose a threat to satellites orbiting Earth. The intense radiation from a solar flare can damage the electronics on board satellites, potentially disrupting services like GPS, weather forecasting, and telecommunications. In severe cases, satellites can be rendered inoperable, leading to significant economic losses. Moreover, solar flares can influence Earth's power grids. The energy from a solar flare can induce electrical currents in power lines, potentially causing transformers to overheat and fail. This can result in widespread power outages, as was the case during the 1989 geomagnetic storm that caused a blackout in Quebec, Canada. In addition to these technological impacts, solar flares can also affect human health. Astronauts in space are particularly vulnerable to the increased radiation levels during a solar flare, as they are outside the protective shield of Earth's atmosphere. This radiation can increase the risk of cancer and other health issues for astronauts on long-duration missions. On Earth, the increased radiation from a solar flare can enhance the natural auroras, also known as the northern and southern lights. These stunning displays of light occur when charged particles from the sun interact with Earth's magnetic field and atmosphere. During a solar flare, the auroras can become more intense and visible at lower latitudes than usual, providing a spectacular show for those lucky enough to witness it. Given the potential impacts of solar flares, monitoring and predicting space weather has become increasingly important. Scientists use a variety of tools and techniques to study the sun and its activity, including solar telescopes, satellites, and computer models. By understanding the mechanisms behind solar flares and their effects on Earth, researchers aim to improve space weather forecasting and mitigate the risks associated with these powerful solar events. But what about the future? As our reliance on technology continues to grow, the importance of understanding and predicting space weather becomes even more critical. Could advancements in technology help us better predict solar flares and their impacts? And how can we protect our infrastructure and astronauts from the potential dangers posed by these solar phenomena? In conclusion, solar flares are a captivating and complex aspect of space weather that can have far-reaching effects on Earth. From disrupting communications and damaging satellites to influencing power grids and enhancing auroras, the impact of solar flares is both fascinating and significant. As we continue to explore and understand the dynamics of our sun, we gain valuable insights into the forces that shape our space environment and their implications for life on Earth. So, the next time you hear about a solar flare, you'll know just how important these cosmic events are to our everyday lives. We delve into the fascinating and tumultuous origins of Earth's only natural satellite, the Moon. This act seeks to unravel the mysteries surrounding how the Moon came to be, exploring various scientific theories that attempt to explain its formation. The Moon has always been a subject of intrigue and speculation, not just for its presence in the night sky, but also for its significant impact on Earth, influencing tides and stabilizing the planet's axial tilt. One of the most widely accepted theories regarding the Moon's formation is the giant impact hypothesis. This theory suggests that the Moon was formed out of the debris left over from a colossal collision between the early Earth and a Mars-sized body, often referred to as Theia. This cataclysmic event is believed to have occurred approximately 4.5 billion years ago, during the early stages of the solar system's development. The impact would have been so intense that it vaporized a significant portion of both celestial bodies, sending molten rock and metal into orbit around the Earth. Over time, this debris coalesced to form the Moon. But what evidence supports this theory? Scientists point to the similarities in isotopic compositions between Earth rocks and lunar samples brought back by the Apollo missions. These samples show that the Earth and the Moon have nearly identical oxygen isotopic ratios, suggesting a common origin. Additionally, the lack of volatile elements in lunar rocks supports the idea that the Moon formed from material that was once part of the Earth, as the intense heat from the impact would have caused these elements to evaporate. However, the giant impact hypothesis is not without its challenges and alternatives. Some scientists propose the double planet hypothesis, which suggests that the Earth and the Moon formed together as a double system from the primordial accretion disk of the Sun. This theory posits that the two bodies formed independently but in close proximity, eventually becoming gravitationally bound. While this theory accounts for some aspects of the Earth-Moon system, it struggles to explain the isotopic similarities between the two. Another intriguing theory is the fission theory, which proposes that the Moon was once part of the Earth and was separated from it due to rapid rotation. According to this hypothesis, the young Earth was spinning so quickly that a portion of its mass was flung off into space, eventually forming the Moon. This theory, however, has largely fallen out of favor due to the lack of evidence supporting such extreme rotational speeds in Earth's early history. The capture theory presents yet another possibility, suggesting that the Moon was formed elsewhere in the solar system and was later captured by Earth's gravity. While this theory could explain some of the differences in composition between Earth and the Moon, it is considered unlikely due to the precise conditions required for such a capture to occur without resulting in a collision or the Moon being flung back into space. As we explore these theories, it is important to consider the role of computer simulations and advanced modeling in testing their viability. Modern technology allows scientists to recreate the conditions of the early solar system, providing valuable insights into the dynamics of planetary formation and the likelihood of various scenarios. These simulations help refine our understanding of the Moon's origins and guide future research. The Moon's formation is not just a question of scientific curiosity. It also holds implications for understanding the history of our own planet. The Moon's gravitational influence has played a crucial role in stabilizing Earth's axial tilt, which in turn affects the planet's climate and seasons. Additionally, the Moon's presence has been a driving force in the evolution of life on Earth, influencing everything from the timing of tides to the behavior of nocturnal animals. As we continue to study the Moon and its origins, we are reminded of the interconnectedness of celestial bodies and the complex processes that shape our universe. The story of the Moon's formation is a testament to the dynamic and ever-changing nature of the cosmos, inviting us to ponder the forces that have shaped not only our solar system, but the countless others that exist beyond our reach. What new discoveries might the future hold as we continue to explore the Moon and its origins? Could there be other factors or events that have yet to be considered in our understanding of the Moon's formation? As we look to the stars and beyond, the quest for knowledge continues, driven by our innate curiosity and desire to uncover the secrets of the universe. We delve into the fascinating world of Mars' moons, Phobos and Deimos. These two small celestial bodies have intrigued scientists and astronomers for centuries due to their unique characteristics and mysterious origins. But what makes these moons so special? And why did they continue to capture our imagination? Phobos and Deimos are the only two natural satellites of Mars, and they are quite different from Earth's moon in several ways. Firstly, they are significantly smaller. Phobos, the larger of the two, measures about 22.4 kilometers in diameter, while Deimos is even smaller, with a diameter of approximately 12.4 kilometers. In comparison, Earth's moon is about 3,474 kilometers in diameter, highlighting just how tiny Mars' moons are. The origins of Phobos and Deimos have been a topic of debate among scientists. There are several theories about how these moons came to orbit Mars. One of the most popular theories suggests that they are captured asteroids. This theory is supported by their irregular shapes and cratered surfaces, which resemble those of asteroids found in the asteroid belt between Mars and Jupiter. However, capturing an asteroid into a stable orbit is a complex process, and scientists are still trying to understand how Mars could have accomplished this. Another theory proposes that Phobos and Deimos formed from debris resulting from a massive impact on Mars. This theory is similar to the one about the formation of Earth's moon, which suggests that a giant impact with a Mars-sized body created a debris disk around Earth that eventually coalesced into the moon. Could a similar event have occurred on Mars, leading to the formation of its moons? Phobos and Deimos also have unique orbital characteristics. Phobos orbits Mars at a very close distance, only about 6,000 kilometers above the Martian surface, making it one of the closest moons to its planet in the solar system. This close proximity causes Phobos to orbit Mars faster than the planet rotates, resulting in it rising in the west and setting in the east, unlike most celestial bodies. In contrast, Deimos orbits at a greater distance, about 20,000 kilometers from Mars, and takes longer to complete an orbit, rising in the east and setting in the west like our moon. The surface features of Phobos and Deimos are also intriguing. Phobos is heavily cratered, with its most prominent feature being the Stickney crater, which is about 9 kilometers in diameter. This crater is so large relative to the size of Phobos that it has significantly altered the moon's shape. Deimos, on the other hand, has a smoother appearance, with fewer large craters, which suggests that it may have experienced a different geological history. The exploration of Phobos and Deimos has been limited, but there have been several missions that have provided valuable data about these moons. The Soviet Union's Phobos program in the late 1980s aimed to study Phobos up close, but the missions faced technical difficulties. More recently, NASA's Mars Reconnaissance Orbiter and other missions have captured detailed images and data, helping scientists to better understand these enigmatic moons. Future missions to Phobos and Deimos are being planned, as these moons could hold clues to the history of the solar system and the processes that shaped it. Additionally, Phobos and Deimos could serve as stepping stones for future human exploration of Mars. Their low gravity and proximity to Mars make them potential sites for bases or way stations for astronauts traveling to and from the Martian surface. As we continue to explore and study Phobos and Deimos, we are reminded of the vastness and complexity of our solar system. These small moons, with their mysterious origins and unique characteristics, challenge our understanding of planetary formation and dynamics. What secrets do they hold? And what can they teach us about the history of Mars and the solar system as a whole? The exploration of Mars moons is a journey into the unknown, filled with potential discoveries that could reshape our understanding of the universe. We delve into the intriguing and unusual rotational dynamics of Venus, the second planet from the Sun. Unlike most planets in our solar system, Venus exhibits a peculiar characteristic. It rotates in the opposite direction to its orbit around the Sun. This phenomenon is known as retrograde rotation. But what causes this backward spin, and what implications does it have for our understanding of planetary motion? To begin with, let's consider what is meant by retrograde rotation. Most planets, including Earth, rotate on their axes in the same direction as they orbit the Sun, which is counterclockwise when viewed from above the Sun's north pole. This is referred to as prograde rotation. Venus, however, rotates clockwise, making it one of the few planets with a retrograde rotation. This means that if you were standing on Venus, the Sun would appear to rise in the west and set in the east, opposite to what we experience on Earth. The reasons behind Venus's retrograde rotation have puzzled scientists for many years. One of the leading theories suggests that Venus might have experienced a massive collision with another celestial body early in its history. Such a collision could have been powerful enough to alter its rotational direction. However, this theory is still debated, as there is no direct evidence of such an impact. Another hypothesis involves the effects of gravitational interactions and tidal forces. Over billions of years, The gravitational pull from the Sun and possibly other planets could have gradually slowed down and reversed Venus' rotation. This process, known as tidal locking, is similar to how the Earth's gravity affects the Moon, keeping the same side facing Earth. However, in Venus' case, the process would have been more complex, potentially involving interactions with the dense atmosphere that Venus possesses. Speaking of Venus' atmosphere, it plays a significant role in its rotational dynamics. Venus has an incredibly thick atmosphere composed mainly of carbon dioxide, with clouds of sulfuric acid. This dense atmosphere creates a phenomenon known as atmospheric superrotation, where the atmosphere rotates much faster than the planet itself. This superrotation could have contributed to the slowing down and eventual reversal of Venus' rotation over time. It's also worth noting that Venus' rotation is extremely slow. A single day on Venus, which is the time it takes for the planet to complete one full rotation on its axis, lasts about 243 Earth days. Interestingly, this is longer than a Venusian year, which is approximately 225 Earth days. This slow rotation, combined with its retrograde motion, results in a very unusual day-night cycle on Venus. The study of Venus' rotation provides valuable insights into the complexities of planetary motion and the various factors that can influence it. Understanding why Venus spins backwards not only helps us learn more about Venus itself, but also sheds light on the dynamics of other celestial bodies and the potential for similar phenomena elsewhere in the universe. As we continue to explore Venus and gather more data through missions and observations, we may uncover more clues about the history and evolution of its rotation. Could there be other planets in distant solar systems with similar retrograde rotations? What does this tell us about the formation and development of planetary systems? These are just some of the questions that scientists aim to answer as they study Venus and its unique characteristics. In conclusion, Venus's retrograde rotation is a fascinating aspect of planetary science that challenges our understanding of how planets evolve and behave. Whether it's due to a colossal impact, gravitational interactions, or atmospheric dynamics, the mystery of Venus's backward spin continues to captivate scientists and enthusiasts alike. As we strive to unravel this enigma, we gain not only a deeper appreciation for Venus, but also a broader perspective on the diverse and dynamic nature of our solar system. Mercury, the innermost planet in our solar system, presents a fascinating landscape marked by numerous craters. These craters are a testament to the planet's tumultuous history and offer insights into the processes that have shaped its surface over billions of years. In this act, we delve into the intricacies of Mercury's craters, exploring their formation, distribution, and what they reveal about the planet's past. Mercury's surface is heavily cratered, much like our Moon. This is primarily due to its lack of a significant atmosphere, which means there is little to no protection against meteoroids and other celestial bodies that collide with it. When these objects strike Mercury, they create craters of various sizes, from small pits to massive basins. But why does Mercury have so many craters, and what can they tell us about the planet's history? The formation of craters on Mercury is a result of impacts from asteroids and comets. These impacts have been occurring since the early solar system, around 4.5 billion years ago. During this time, the solar system was a chaotic place, with numerous objects colliding with each other. Mercury, being so close to the Sun, was particularly vulnerable to these impacts. The lack of an atmosphere means that even small meteoroids can reach the surface and create craters, unlike on Earth, where many burn up upon entry. One of the most significant craters on Mercury is the Caloris Basin. This massive impact crater is about 1,550 kilometers in diameter and is one of the largest impact basins in the solar system. The formation of the Caloris Basin was a monumental event in Mercury's history, likely caused by a massive asteroid impact. The energy released during this impact was so immense that it caused the surface on the opposite side of the planet to become jumbled and chaotic, a region now known as the Weird Terrain. But how do scientists study these craters, and what tools do they use to map Mercury's surface? The primary method of studying Mercury's craters is through spacecraft missions. NASA's MESSDNGER mission, which orbited Mercury from 2011 to 2015, provided a wealth of data about the planet's surface. MESSDNGER was equipped with a suite of instruments, including cameras and spectrometers, which allowed scientists to map the surface in unprecedented detail. The data from MESSDNGER has been crucial in understanding the distribution and characteristics of Mercury's craters. Through these observations, scientists have been able to categorize craters based on their size and morphology. Simple craters, which are small and bowl-shaped, are the most common type on Mercury. As craters increase in size, they become more complex, often featuring central peaks or rings. The largest craters, like the Caloris Basin, are classified as impact basins and can have multiple rings and extensive ejecta blankets. The study of Mercury's craters also provides insights into the planet's geological history. By analyzing the density and distribution of craters, scientists can estimate the relative ages of different regions on the planet. Areas with a high density of craters are typically older, as they have been exposed to impacts for a longer period. Conversely, regions with fewer craters are younger, suggesting more recent geological activity that may have resurfaced the area. Another intriguing aspect of Mercury's craters is the presence of hollows. These are shallow, irregular depressions found on the floors and rims of some craters. Hollows are unique to Mercury and are thought to be formed by the sublimation of volatile materials, possibly due to the intense solar radiation the planet receives. The discovery of hollows has added a new layer of complexity to our understanding of Mercury's surface and its geological processes. The study of Mercury's craters is not just about understanding the planet itself, but also about gaining insights into the early solar system. The cratering record on Mercury provides a window into the period known as the Late Heavy Bombardment, a time when the inner planets were heavily bombarded by asteroids and comets. By studying the craters on Mercury, scientists can learn more about the frequency and scale of these impacts, which in turn helps us understand the conditions that shaped the early solar system. In conclusion, Mercury's craters are more than just scars on the planet's surface. They are a rich source of information about the planet's history and the early solar system. Through spacecraft missions and detailed mapping, scientists continue to uncover the secrets hidden within these craters, piecing together the story of Mercury's past. As we continue to explore and study this enigmatic planet, what new discoveries await us beneath its cratered surface? What more can these ancient impacts tell us about the formation and evolution of our solar system? The journey to uncover Mercury's mysteries is ongoing, and each crater brings us one step closer to understanding the complex history of the innermost planet. We delved into the fascinating world of Mercury, the innermost planet in our solar system. Mercury's surface is a testament to the violent and dynamic history of our solar system. It is covered with craters, much like our moon, which are the result of countless impacts from asteroids and comets over billions of years. These craters vary in size, with some being just a few meters across, while others span hundreds of kilometers. The mapping of these craters provides valuable insights into the age and composition of Mercury's surface, as well as the history of the solar system itself. By studying these features, scientists can infer the processes that have shaped not only Mercury, but also other rocky planets. This exploration of Mercury's craters has been made possible by spacecraft missions, such as NASA's MESSDNGER, which orbited Mercury and provided detailed images and data about its surface. Understanding Mercury's craters is crucial for piecing together the planet's geological history and for comparative planetology studies. Now, we transition to Act 26, titled Jupiter's Magnetosphere, where we shift our focus from the rocky surface of Mercury to the vast and powerful magnetic field of Jupiter. Jupiter, the largest planet in our solar system, possesses the most extensive and intense magnetosphere of any planet. But what exactly is a magnetosphere, and why is Jupiter so significant? A magnetosphere is a region of space surrounding a planet where charged particles are controlled by that planet's magnetic field. Earth's magnetosphere, for instance, protects us from the solar wind, a stream of charged particles emitted by the sun. Jupiter's magnetosphere, however, is on a much grander scale. It extends millions of kilometers into space, far beyond the orbit of its moons, and is shaped by the planet's rapid rotation and powerful magnetic field. Jupiter's magnetic field is generated by the movement of metallic hydrogen within its interior. This movement creates a dynamo effect, similar to how Earth's magnetic field is generated by the movement of molten iron in its outer core. However, Jupiter's magnetic field is much stronger than Earth's, about 20,000 times more powerful, and its magnetosphere is the largest structure in our solar system, even larger than the Sun itself. The exploration of Jupiter's magnetosphere has been a key focus of several space missions. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, is specifically designed to study the planet's magnetic field and its magnetosphere. Juno's instruments measure the magnetic field's strength and direction, providing a detailed map of its structure. This data helps scientists understand the processes occurring within Jupiter's interior and how they contribute to the planet's magnetic field. One of the most intriguing aspects of Jupiter's magnetosphere is its interaction with the planet's moons, particularly Io, Europa, and Ganymede. Io, the most volcanically active body in the solar system, emits a significant amount of sulfur dioxide gas, which becomes ionized and forms a plasma torus around Jupiter. This plasma interacts with Jupiter's magnetic field, creating intense auroras at the planet's poles, similar to the northern and southern lights on Earth, but much more powerful. Europa, another of Jupiter's moons, is of particular interest because it is believed to have a subsurface ocean beneath its icy crust. The interaction between Europa's surface and Jupiter's magnetosphere could provide clues about the moon's potential habitability. Ganymede, the largest moon in the solar system, is unique because it has its own magnetic field, which interacts with Jupiter's magnetosphere in complex ways. The study of Jupiter's magnetosphere is not only important for understanding the planet itself, but also for gaining insights into the magnetic environments of other planets and exoplanets. By studying Jupiter, scientists can develop models that help predict the magnetic fields of planets outside our solar system, which is crucial for understanding their atmospheres and potential habitability. Jupiter's magnetosphere also plays a role in shaping the planet's radiation environment. The intense radiation belts within the magnetosphere pose challenges for spacecraft and potential future human exploration. Understanding the dynamics of these radiation belts is essential for designing missions that can safely navigate this harsh environment. As we continue to explore Jupiter's magnetosphere, we are reminded of the vastness and complexity of our solar system. The study of this giant planet's magnetic field not only enhances our understanding of Jupiter, but also provides a window into the processes that govern magnetic fields throughout the universe. What new discoveries await us as we probe deeper into Jupiter's magnetic realm? How will these findings shape our understanding of other planets and the potential for life beyond Earth? The exploration of Jupiter's magnetosphere is a journey into the unknown, filled with the promise of new knowledge and insights into the workings of our solar system and beyond. We delve into the intriguing and somewhat mysterious ring system of Neptune, the outermost planet in our solar system. While Neptune's rings may not be as prominent or well known as those of Saturn, they hold their own unique place in the study of planetary rings and offer fascinating insights into the dynamics and history of our solar system. Neptune's rings were first discovered in 1984 by a team of astronomers using ground-based telescopes. However, it wasn't until the Voyager 2 spacecraft flew by Neptune in 1989 that the rings were observed in greater detail. Voyager 2 provided the first close-up images of Neptune's rings, revealing a complex and faint ring system that had previously been difficult to study from Earth. Neptune's rings are composed primarily of dust and small particles, which makes them much fainter and less dense than the rings of Saturn. This faintness is one reason why they were not discovered until relatively recently. The rings are also relatively narrow and dark, which adds to the challenge of observing them from Earth-based telescopes. The ring system of Neptune consists of 5 principal rings, named after astronomers who made significant contributions to the study of the planet: Gall, Leverrier, Lassell, Arago, and Adams. These rings vary in width and density, with some being more prominent than others. The Adams ring, for example, is one of the more notable rings due to its peculiar clumpy structure, which is thought to be caused by gravitational interactions with Neptune's moons. One of the most intriguing features of Neptune's rings is the presence of ring arcs within the Adams ring. These arcs are bright, dense clumps of material that appear to be confined to specific regions of the ring. The existence of these arcs puzzled scientists for some time, as they seem to defy the expectation that material in a ring should be evenly distributed. It is now believed that the gravitational influence of Neptune's moon, Galatea, plays a crucial role in maintaining these arcs, preventing them from spreading out and dissipating. The composition of Neptune's rings is another area of interest for scientists. The rings are thought to be composed of ice particles coated with silicates or carbon-based materials, which give them their dark appearance. This composition is similar to that of the rings of Uranus, another ice giant in our solar system, suggesting that there may be common processes at work in the formation of rings around these distant planets. The origin of Neptune's rings is still a subject of research and debate. One hypothesis is that the rings are relatively young and may have formed from the debris of a moon or comet that was shattered by a collision or tidal forces. Another possibility is that the rings are remnants of the primordial material from which Neptune and its moons formed, although this would imply that the rings have been stable over billions of years. Neptune's rings also offer a window into the dynamic interactions between the planet and its moons. The gravitational forces exerted by Neptune's moons, particularly the inner moons, play a significant role in shaping the structure and stability of the rings. These interactions can lead to phenomena such as the confinement of ring arcs and the creation of gaps within the rings. Studying Neptune's rings not only enhances our understanding of this distant planet, but also contributes to our broader knowledge of ring systems in the solar system. By comparing the rings of Neptune with those of other planets, such as Saturn, Jupiter, and Uranus, scientists can gain insights into the processes that govern the formation and evolution of rings. This, in turn, can inform our understanding of the early solar system and the conditions that led to the formation of planets and their satellites. As we continue to explore the outer reaches of our solar system, Neptune's rings remain a captivating subject of study. Future missions and advancements in telescope technology may provide even more detailed observations of these faint rings, shedding light on their composition, structure, and origins. What secrets do these distant rings hold, and what can they tell us about the history and dynamics of our solar system? As we seek answers to these questions, Neptune's rings continue to be a source of fascination and discovery. We turn our attention to the intriguing moons of Uranus, a planet that stands out in our solar system due to its unique axial tilt. Unlike most planets, which rotate more or less upright in relation to their orbits, Uranus is tipped over on its side, with an axial tilt of about 98 degrees. This unusual orientation gives rise to extreme seasonal variations and has a significant impact on its moons and rings. Uranus is orbited by 27 known moons, each with its own distinct characteristics and stories. These moons are primarily named after characters from the works of William Shakespeare and Alexander Pope, a tradition that adds a layer of cultural richness to our understanding of the solar system. But why are these moons so fascinating, and what makes them stand out in the vast expanse of space? Let's start with the largest of Uranus' moons, Titania. Discovered by William Herschel in 1787, Titania is the 8th largest moon in the solar system. It is composed of roughly equal parts ice and rock, and its surface is marked by a mix of craters and canyons. One of the most notable features on Titania is the Messina Chasmata, a massive canyon system that stretches for about 1,500 kilometers. Imagine the Grand Canyon, but on a moon millions of kilometers away. Next, we have Oberon, another large moon discovered by Herschel at the same time as Titania. Oberon is slightly smaller than Titania and shares a similar composition of ice and rock. Its surface is heavily cratered, suggesting an ancient landscape that has remained largely unchanged for billions of years. Among its craters, the Hamlet crater stands out, with a diameter of about 206 kilometers. What secrets might these craters hold about the history of the solar system? Miranda, one of the smaller moons, presents a particularly intriguing case. It is known for its bizarre and varied surface, which includes features such as the Verona Rupes, a cliff that may be the tallest in the solar system, with a height of up to 20 kilometers. Miranda's surface appears to have been reshaped by geological activity, leading to a patchwork of ridges, valleys, and cliffs. What forces could have sculpted such a unique landscape? Ariel and Umbriel, two other significant moons, also offer fascinating insights. Ariel is the brightest of Uranus' moons and has a surface characterized by canyons and ridges, suggesting the history of tectonic activity. Umbriel, on the other hand, is the darkest of the major moons, with a surface that appears to be covered in a layer of dark material. What could cause such differences in appearance between these neighboring moons? The moons of Uranus are not only interesting for their physical characteristics, but also for what they can tell us about the history and evolution of the solar system. The diverse surfaces and compositions of these moons suggest a complex history of formation and geological activity. Could studying these moons help us understand more about the processes that shaped the early solar system? In addition to the major moons, Uranus is surrounded by a collection of smaller, irregularly shaped moons. These moons, such as Caliban, Sycorax, and Prospero, are thought to be captured objects, possibly originating from the Kuiper Belt or beyond. Their irregular shapes and distant orbits add another layer of mystery to the Uranian system. How did these moons come to be captured by Uranus, and what does their presence tell us about the dynamics of the outer solar system? The exploration of Uranus and its moons has been limited, with the only close-up observations coming from the Voyager 2 spacecraft in 1986. Since then, advances in telescopic technology have allowed astronomers to continue studying these distant worlds from afar, but many questions remain unanswered. Could future missions to Uranus provide new insights into these enigmatic moons and their parent planet? As we delve deeper into the mysteries of Uranus moons, we are reminded of the vastness and complexity of our solar system. Each moon, with its unique features and history, offers a glimpse into the processes that have shaped the planets and moons we see today. What new discoveries await us as we continue to explore the outer reaches of our cosmic neighborhood? In the next act, we will continue our journey through the solar system, exploring the fascinating world of Neptune's moons. What secrets do these distant satellites hold, and how do they compare to the moons of Uranus? Join us as we uncover the mysteries of the outer planets and their captivating companions. We explored the fascinating moons of Uranus, each with its own unique characteristics and stories. Uranus, known for its dramatic tilt, hosts a collection of moons with intriguing names and features, such as Miranda, Ariel, and Titania. These moons offer a glimpse into the complex and varied nature of the celestial bodies that orbit the planets in our solar system. We turn our attention to the Sun, the central star of our solar system, and delve into the intriguing phenomenon known as solar cycles. The Sun, a massive ball of hot plasma, is not just a constant source of light and heat. It is also a dynamic and ever-changing entity. One of the most significant patterns of change observed in the Sun is the solar cycle, an approximately 11-year cycle that affects solar activity. But what exactly is a solar cycle, and why does it matter? The solar cycle is a periodic change in the Sun's activity and appearance, including variations in the number of sunspots, solar flares, and other solar phenomena. This cycle is driven by the Sun's magnetic field, which undergoes a regular process of winding up and unwinding, leading to changes in solar activity. The solar cycle begins with the solar minimum, a period of low solar activity characterized by a minimal number of sunspots. Sunspots are temporary phenomena on the sun's photosphere that appear as spots darker than the surrounding areas. They are caused by the sun's magnetic field and are often associated with solar flares and coronal mass ejections, CMBs. As the cycle progresses, the number of sunspots increases, reaching a peak known as the solar maximum. During this time, the sun is more active, and we observe more solar flares and CMEs. Why is it important to understand the solar cycle? The sun's activity has a direct impact on space weather, which can affect satellite operations, communication systems, and even power grids on Earth. For instance, during periods of high solar activity, the increased number of solar flares and CMEs can lead to geomagnetic storms. These storms can disrupt satellite communications, cause power outages, and even affect the accuracy of GPS systems. Moreover, the solar cycle has implications for climate studies. While the sun's energy output does not change significantly over the cycle, the variations in solar activity can influence Earth's climate system. Scientists study these cycles to better understand the sun's role in climate change and to improve climate models. How do scientists study solar cycles? Researchers use a variety of tools and techniques to monitor the sun's activity. Ground-based observatories and space-based telescopes, such as the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO, provide valuable data on sunspots, solar flares, and other solar phenomena. These observations help scientists track the progress of the solar cycle and predict future solar activity. One of the key indicators of the solar cycle is the sunspot number, which is a measure of the number of sunspots visible on the sun's surface. By tracking the sunspot number over time, scientists can identify the phases of the solar cycle and make predictions about future solar activity. Additionally, scientists study the sun's magnetic field, which plays a crucial role in driving the solar cycle. The magnetic field undergoes a process called the solar dynamo, which generates and maintains the sun's magnetic field and is responsible for the cyclical nature of solar activity. As we continue to study the solar cycle, we gain a deeper understanding of the sun's behavior and its impact on our solar system. This knowledge is crucial for preparing for and mitigating the effects of space weather on our technology-dependent society. By understanding the solar cycle, we can better predict solar storms and develop strategies to protect our satellites, communication systems, and power grids from potential disruptions. In conclusion, the solar cycle is a fascinating and complex phenomenon that plays a significant role in shaping the environment of our solar system. By studying the solar cycle, we not only gain insights into the sun's behavior, but also enhance our ability to predict and respond to the effects of solar activity on Earth. As we continue to explore the mysteries of the sun and its cycles, we are reminded of the intricate connections between our star and the planet we call home. What new discoveries will future solar cycles reveal, and how will they shape our understanding of the sun and its influence on our world? We delved into the fascinating world of solar cycles, specifically focusing on the sun's 11-year activity pattern. This cycle is a period during which the sun's magnetic field undergoes a complete flip, meaning the magnetic north and south poles switch places. This cycle is significant because it affects solar activity, including the number of sunspots, solar flares, and coronal mass ejections. These activities can have profound effects on space weather, which in turn can impact satellite operations, communication systems, and even power grids on Earth. The solar cycle is a crucial aspect of understanding our sun, as it helps scientists predict solar activity and prepare for its potential impacts on our technology-dependent society. We turn our attention to the heliopause, a concept that marks the boundary where our solar system ends. The heliopause is the outermost layer of the heliosphere, which is a vast bubble-like region of space dominated by the solar wind, a stream of charged particles emanating from the sun. The heliosphere acts as a protective shield for our solar system, deflecting cosmic rays and interstellar radiation. But what exactly is the heliopause, and why is it important? The heliopause is the point where the solar wind slows down and balances with the interstellar medium, which is the matter and radiation that exists in the space between star systems in a galaxy. Beyond the heliopause lies interstellar space, a region filled with material from other stars and the remnants of ancient supernovae. The heliopause is not a fixed boundary. It fluctuates depending on the solar wind strength and the pressure of the interstellar medium. One might wonder, how do we know where the heliopause is located? The answer lies in the data collected by spacecraft such as Voyager 1 and Voyager 2. These spacecraft, launched by NASA in 1977, have been traveling through space for over 4 decades and have provided invaluable information about the outer reaches of our solar system. In 2012, Voyager 1 became the first human-made object to cross the heliopause and enter interstellar space, followed by Voyager 2 in 2018. The data from these spacecraft have helped scientists understand the nature of the heliopause and the transition from the solar wind-dominated region to the interstellar medium. The heliopause is a dynamic and complex region, influenced by various factors such as the sun's activity, the solar cycle, and the interstellar environment. It is not a smooth boundary, but rather a turbulent region where the solar wind and interstellar medium interact. This interaction creates a shockwave known as the termination shock, where the solar wind slows down abruptly before reaching the heliopause. Beyond the heliopause lies the bow shock, a region where the interstellar medium is deflected by the heliosphere's movement through the galaxy. Understanding the heliopause is crucial for several reasons. Firstly, it helps us comprehend the extent of our solar system and the influence of the sun's activity on its boundaries. Secondly, studying the heliopause provides insights into the nature of the interstellar medium, which is essential for understanding the broader galactic environment. Lastly, the heliopause serves as a natural laboratory for studying the interactions between stellar winds and interstellar material, which can be applied to other star systems and contribute to our knowledge of the universe. The exploration of the heliopause also raises intriguing questions about the future of space exploration. As we continue to send spacecraft further into space, what challenges will we face in navigating the complex and dynamic regions beyond our solar system? How will the knowledge gained from studying the heliopause inform the design and operation of future interstellar missions? These questions highlight the importance of continued research and exploration of the heliopause and beyond. In conclusion, the heliopause represents a fascinating and critical boundary in our understanding of the solar system and its interaction with the interstellar environment. It marks the transition from the solar wind-dominated region to the vast expanse of interstellar space, offering valuable insights into the nature of our cosmic neighborhood. As we continue to explore and study this boundary, we gain a deeper understanding of the universe and our place within it. The heliopause is not just a boundary. It is a gateway to the unknown, inviting us to explore and discover the mysteries that lie beyond.